Okay, so I think actually these QR codes will give you some hint for about the QR codes what you have right now, I think. Does it work?
If anyone's missing a QR code, it's me. It's going to have.
Let's see.
Is it the same QR code or
No, they're different. Yeah, it's different. So actually this is a hint about what you guys are having now. Maybe, yeah, it's just a hint, so let's go for about the introduction. Okay, I believe that the reason is so important for all of us about actually what we are doing here for the ZK. So I would love to introduce actually my reason that I studied the crypto-related works from 2017 because 2017 was a big had a really big impact in my life. That I had two things at the time. The first one is about the open source, and the second is about let's say about the open source first. So by the way, I was a kind of a serial entrepreneur, and I actually founded a startup in 2012 with my friends, and it was kind of a basic classification algorithm using support vector machine with the machine learning, which is and actually that was acquired by some AI startup in 2014 because there was a big quantum jump in machine learning via deep learning in 2013. And I, in that company, because I was kind of a acquired person, so it was pretty weird that it was a big company. Like we had like 50 people there, and to me it seemed like nobody works there. So there was no hunger at all. So I was curious, why people are just spending their young days here? So they are all talented people, but they're just not working. I mean, they're not just putting themselves into some tough situation or etc. So I was actually I struggled a lot there because I really couldn't understand, and I realized that the incentive model is totally different. My case and them, because if we actually found a startup, we can imagine like, hey Mo, you are the kind of a founder and I am the 10th member of your company. Then what about how was the gap between your incentive and me?
A very big gap.
Yeah. How much times? How many times?
Maybe 100 times.
Yes, exactly. Because founder will have a kind of a 50% of the shares, and the 10th member will have kind of a 0.5, less than 1%. So it's exactly 100 times. But founders actually should motivate people and should keep sweet talks, and we should motivate like, we can make a bright future together. But actually, I'm making 100 times the incentive to you compared to you. So people started to realize there's the actual big incentive gap between the shareholders and the employees. And I thought that was some reason that I couldn't understand why people are working there. And during that time, I just discovered a wonderful community, the open source community, and about the Linux. Because I was actually I developed some operating system which is run by something like ChatGPT at the time. So based on language model, made an open source based operating system, and it was the main reason why I got into the open source community at the time. And it was so amazing because people just the culture is so different. I mean, let's think about we have two projects, project A and project B. And if we do a company, does it make sense that when they compete with each other, does it make sense that project A, I mean company A helps company B? It's a stupid thing. It doesn't make sense at all. But in open source culture, actually, if there are two different libraries and people, and actually they help each other. So I just saw that, oh, actually this is something where the positive sum game starts. And also, if you think about the top 20 companies in the world, then 20 years ago it was all about the energy companies, but for right now, all of the software companies. And it implies that software source code is one of the powerful means of production. And open source is something kind of a communism there. I mean, people are so like donating and making the means of production as a public good. Actually, it's different with the community model, but it was really fascinating to me because, I mean, I am not saying that the capitalism-based startup model is bad. I mean, these two models are different with each other, and it was just so fascinating for me because it was too different. Because I was kind of burnt out during the startup game, just competing and just putting my 200% into the game, etc. So, yeah, that was my big moment for me in 2017. And another big moment was about this guy. Yeah, because interestingly, I just saw the documentary in 2017. I actually were aware of what happened, but I just saw the documentary. Yeah, I'm not sure it was via Netflix, but I just saw the documentary in 2017, and actually, it was kind of a mind-blowing moment for me. So maybe many of us are aware of who is Edward Snowden, right? But yeah, just quickly sharing, he revealed a secret project from the intelligence as an intelligence agent in the US that the US was actually, I think they might still doing that. So actually, before Edward Snowden's end-to-end encryption movement, actually it was pretty common to access to HTTP without the secure communication. So we just access to some website with HTTP without HTTPS. Actually, it's not an encrypted thing, so actually we can extract some values when you communicate with some servers. And via the undersea cables, the US intelligence, NSA and CIA, actually they are monitoring them and label every information of each individual. There was that project, and what Edward Snowden did was actually just collecting some evidence of actually what the US is actually doing under the sea. I mean, and then he revealed actually we are living in the real dystopia. And because of that, actually he studied the end-to-end encryption movement, and it was also a huge moment for me at the time. And these two combination, I mean, the open source community and the cypherpunk community, where these two things are combined, was a Ethereum community at the time for me. So I started to work as an independent researcher just to solve these kind of problems from there. And these, maybe have you heard of this store now? This is anything? Do you know? Do you have any hint what it is? It is about the post-quantum computation. So, if you have enough quantum computing power, then everything that we are communicating is based on the elliptic curve cryptography, and then actually they might be able to be decrypted. Then in the future, actually, I can say that we are actually living in a dystopia for right now, but we may live in a latent dystopia until we have a solution for the post-quantum cryptography, because with the advent of the AGI and the AI, then it'll be able to process all the communication real time by decrypting that using quantum computation and then label them and store them. It's possible. I think it's not that far from here. Like maybe in 10 years, it will be able to label everyone with post-quantum computation and AI, definitely. So it's a real threat. So privacy is one of the really important human rights. It's also declared human rights by the UN. And if you think about the percentages of we are spending in the digital world, then it's definitely we are on the trend that we are migrating our world to the digital world, comparing to our parents' generation and grandparents' generation. Actually, the trend is so obvious that we are spending more and more time in the digital world. Then, so we can say that we are migrating our lives to a new territory. And we are kind of the pioneer of this exploration. And what do you see in this new territory? What does it look like? For me, it's kind of it's so wild. There are so many criminal activities, there are so many cyberbullying, and in the dark web, actually, we can see a lot of some prevalent criminals Then how can we prevent this? What do you think? How can we prevent this? Yeah, actually, don't say the answer, but yeah. The easiest way is actually definitely adding some regulations, like for example cyberbullying. We can add some regulations, but actually the world actually works like that. So here's another example that this is some event last year happened in Seoul, South Korea. Some people actually painted on a palace wall, and actually they got caught in a day, because in Seoul there are all the CCTVs around there, and it's really easy to find people. And Korean people actually do not think this is as a problem. We are so used to this situation, and we have a trust that this system will work correctly in the right way. So it's something kind of trusting the authority. But what happens if the police and the authorities are compromised? Then it's actually really easy to get shifted to some trustworthy looking authority to a big brother. So as Wanseob said, we actually have a solution to resolve this kind of problem. So what I mean is, it's about the programmable cryptography. I can say something, an example like when we, if you have some clocking jacket, then actually you can do many things there. But actually, this is actually adding you the privacy. But while you're just getting clocked, then you can prove yourself that you are doing any harmonious activities while you're wearing this jacket with programmable cryptography. This is something what we can do. I want to give you a more detailed example, like when we send some messages via Instagram, then let's say it's a full of curse words. Then how can we prevent that? Maybe letting Instagram censor that and block it. It's the dystopian approach. It is a dystopian approach. The utopian approach is that we encrypt the message, and then maybe you can give some proof to the Instagram that it doesn't have any harmful content inside of it. But what if because it means that you know the algorithm, because you are proving yourself. So it's kind of zero knowledge, but actually you know the algorithm, so it might be easy to actually tweak the content a little bit until it says true. It's kind of a basic, actually, attack scenario of the zero knowledge. And to resolve this problem, maybe we can also use a little bit different approach. So you encrypt your message and send it to Instagram. And then Instagram will actually put this into a machine learning model, which can be worked also in a homomorphically encrypted form. Then it should be able to output the result without actually decrypting the message. This is actually how we can use fully homomorphic encryption to the real world use case. That Instagram can block some sensitive or harmful content without actually checking the exact content of the message. So this is the way where we can use the cryptography, but this is something kind of a Manhattan project. Yeah, it's a really sadly, all of the founders are now in jail. Actually, they are also our friends, and they are also the pioneers of this new territory. And what I want to say is that when we deal with the privacy technology and cryptography, cryptography is a weapon to protect ourselves in the digital world. This is kind of a only weapon that we can use. And then it also is a tool. It's definitely double-edged. So when you think about the anonymity, it can be used in a dark way too, because Tornado Cash was the main channel for Lazarus for their money laundering from North Korea. And in the dark web, there's so many the criminal content in the dark web. So if we think about the responsibilities, then actually researchers are completely free from the responsibility. I think it's really difficult to say we are completely free, because we know the potential, and actually if we know that, we need to find a better solution that we can resolve all the problems. This is the way how we can use this weapon in a safer way and making our utopia in a much more safer world. So yeah, but yeah, actually, as the history just repeat as Oppenheimer was charged, and founders of the 200 fish world are also getting charged for the yeah.
I think the court case is still going on, right? Or you are already in the jail for the tornado catch people.
Mhm.
Are they already in the jail? Or
Yeah, they are in jail.
They're in custody, yeah. There's no judgment, right? Well, there's judgment for one of the cases.
Yep.
They're arresting him.
Because my project, the reason why I started working at the PSA was building a private transaction protocol on top of Ethereum. It's kind of implementing Zcash as a layer 2 on top of Ethereum. So we all were aware of these situations, and yeah, people, the Tornado Cash people, they bravely actually executed their plan, and now are getting charged. Yep. Okay, so this is my thoughts for about the privacy and the Ethereum and the. I mean, Ethereum is our new territory, where actually, yeah, I just got interested a little bit some interesting idea here that Ethereum is a universe, and that is the reason why we can migrate our lives into the Ethereum, which means that the universe actually has a potential to have a universe with a live cat or a dead cat. And the quantum physics decide that. The determinism is actually by the quantum physics in Ethereum. The cryptographic inventions like proof of work or proof of consensus actually alternate the determinism there. So if you don't have the determinism, then actually I cannot send some transaction there, because there's no way that I can determine a future that actually some $10 goes to Mo. Yeah. So determinism is one of the most important feature of the universe, and because Ethereum is offering the determinism by the cryptographic invention, we can migrate to the Ethereum as a really a digital universe. So yeah, so these are my thoughts and my introduction. That's why I am doing all of these things and etc. And I think that the cryptography is like zero knowledge and multi-party computation and fully homomorphic encryption. Actually, they will play crucial roles to save us from the current dystopia. So this is the mission, and I think that many people's mission is pretty similar here, that saving ourselves from the kind of a dystopian approaches or dystopian reality or etc. So yeah, it was my introduction, and okay. Then yeah, let's go back to. Actually, you don't need to take a QR. This is about the QR that I showed at first. Did you get any hint what it is? Yeah. Did you get?
Is it in the bytecode?
It's not a
private key for the account.
yeah, maybe.
Whoever is first gets the ether.
I'm sorry.
Whoever is first gets the ether.
Yeah, you may get. Actually, I put only a bit of the 0.01. It'll cover your like some cups of coffee. Yeah. So let's see. Actually, who can drain that ether there? Yeah. So yeah, we're gonna move for our first part. Okay.
Sorry, I have a question.
Yes.
Does this QR code has to do with that QR code? I'm confused. Like, what was
You need to figure out.
I need to figure out.
Yeah. Okay. Okay, great. Actually, today's session will be consisting like I do explain the main concepts, and we're gonna have a breakout groups. We're gonna have a 4 to 5 breakout groups, and in the breakout group, you need to explain that by yourself to others. Yeah. So actually, if you cannot explain yourself, it's something that you are not knowing exactly. So we should be able to explain something by yourself, definitely. And yeah. So it starts from the. Just a moment, please. It'll be something kind of a speed run. I hope that we can cover all the things for the next 3 days. And yeah, let's see.
Quick question. Are we gonna get the links to the slides?
I'm gonna give you the link after having this explanation. It'll be kind of your reference for when you try to explain something by yourself. Okay, let's go. Yep. What does it look like?
Sorry. This is encrypted, right?
Yeah, it's a definitely encrypted form. What does it look like?
Is it L or T? Sorry, I.
I. It's I. Yep. Would you please try to decrypt that? Any hints? Any hint? The QR code was a kind of a hint. Yeah, it was kind of. Actually, it has a hint inside of it.
How is that?
It's not Caesar.
It's not Caesar.
Is it cipher?
Try that. Try that.
Do you use that as the key to access the solution?
No, I didn't.
Wait, I think X and Y are the points for the electrical one.
You mean the QR code?
Yeah.
Maybe.
Is this a prime number?
No, they are not. You mean the QR code?
This one.
This one? No, it's not a prime number.
Is it a number?
Maybe I can give you a hint. And yeah, the title of the part 1 is the hint, I guess.
It is Caesar.
Yeah.
And it's even the default one when you fill in.
So what's the answer?
Hold on. So it's
Group, yeah.
Is that group?
Yeah, it is about growth.
24 shifts?
24 shifts.
Just
Yeah, actually it's actually growth. Yeah. And actually it was a Caesar cipher. Yeah. So maybe who is not familiar with the Caesar cipher? It's just a shifting. Actually, it's a having a map that shifts like in our case a shifting 24, right? Yeah. So for example, let's say hello. Then let's say we have a shift with 1 and I F M P is a new encrypted form of a hello. Then actually we can learn many things from Caesar cipher there because Caesar cipher is actually a group. I mean, I will gonna explain actually what is group exactly. So group is a set. So Caesar cipher has a set with alphabet. So group is a set, but actually it's something that you can do some arithmetic calculations inside of it, and or maybe we actually say that as a binary operation. So for example, let's say you are not combining. Let's say each of the alphabet corresponds to number from 1 to 26. Is it correct? We have 26 letters, right? So 1 to 26. And then let's say that we are shifting that. For example, let's say A shifting A should be B. A shifting B should be C, like this. So it's all about, okay, we have a group and we are doing some binary operations, picking a 2 elements from the group and making a result. And then what is the constraint for group? The result should be also an element for the group, for the set. So if we say like A and shift something like B, and it becomes a some Korean word. It actually is not a group because it's not closed inside of that. So the closure is one first feature of the group, one constraint for a group, and actually there exists. You can just think about the number and the addition. That we have a associativity and identity and the inverse, just like addition operation with number with integers.
Is it necessary to have only binary operations, or can
Yeah.
you do like other operations?
Only binary operation. Yeah. Okay. So this is a definition of a group. And here's some simple questions. Now let's think about those cases. So the bold Z actually says the all set of all integers, and then the Q star is a all non-zero rational numbers. Then are they group? So integers and plus is that group?
No.
Yes, that's a group, yeah.
Okay. What about integers and multiplication?
Yes.
Yes.
That's group, right?
Yes.
Yeah.
Okay. Yeah. And about non-zero rational numbers and multiplication. Do they have a non-zero? Non-zero.
No.
Yes.
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 Right. Yeah.
Yes.
So they are actually satisfying all these four conditions, then we can say them as they are in a group. They are a group. The set is a group. Okay, and then let's think about the Caesar cipher in.
Yeah.
Actually, I already told Caesar cipher is a group, but yeah. Caesar cipher is a really interesting example of how to express a cipher with the relation with the abstract algebra, because how the elliptical cryptography works is exactly how this Caesar cipher works, because we all just handling the groups. I'm gonna explain a little bit more in detail that, let's say Caesar cipher, the alphabet is corresponding to number there. Then we are defining an encryption operation as a just plus and modularize it with the size of the group set. And then definitely because all the results is close and we have the associativity, identity, inverse. So actually, the Caesar cipher can be called as a group because it's just we are modularizing and then having an addition operation there. Let's see actually what exactly happens there. This is how the Caesar cipher works. So A plus H mod 26. Is that correct?
Zero
Yeah.
plus H, right?
Yeah.
Yeah.
So yeah, I think it's correct.
Yeah.
It's correct. Yeah, great. But you know, it's we can easily decrypt Caesar cipher, isn't it?
Yes.
Mm.
Yeah, it's pretty easy to decrypt the Caesar cipher. And how can you make it in a more difficult version?
Increase the size of the set.
Increase the size.
I think instead of being additive, we can be using multiplicative.
Definitely. So actually, if we try to define a multiplicative thing, then it might be much more difficult than just an addition. So let's see. Actually, I picked a prime number Q there, and the number is 29. And because I needed a little bit more some other characters, I just added another alphabet letters there. And let's try to define our mapping from alphabet. Let's try to define the encryption operation as below. So we are actually mapping the alphabet using the G. So G to the A actually becomes a mapped number, for example. Then we are defining an encryption operation just like below that. A encryption K is a G to the A times G to the K, and modularize that with 29, okay, prime number 29. Let's see actually what happens there. Okay. So, yeah. I just picked a generator G to 19 there. And then 19 to the 1 mod 29 is actually maps to S. And then 19 to B mod 29 maps to M. Actually, you can see that it's a much more difficult to think about the pattern here. but actually we can define the binary operation. Actually, we are just designing that. We don't need to think about what is addition or what is multiplication. Addition and multiplication is just a concept that we know for right now, and we are just designing a binary operation. That's all.
Why did you take 29 mod 29 then?
Actually, it is related to the number theory, and the prime numbers makes the modular circle. So,
But then we only have like 26 alphabets, so I'll be repeating ABC again.
actually, so because of that, I added a new letters there.
Right. Oh, okay.
Yeah, I added some new letters like
A with the
yeah,
circle.
A.
Ah, okay.
I don't know actually how do I call that, but
Don't you need three? Sorry, I was just thinking, don't you need three new letters?
actually it's a multiplicative group, so actually we should
It's
Right,
remove
like
zero.
because, yeah, okay.
Yeah. Yep. Then
So essentially, we are just treating the, so what you're saying is, instead of treating it as a multiplicative group, we are treating it as some set with just some operation that, in this case, allow us to map a value
Right.
in the group to another, right? Another set to another.
so we are
No, I finished.
So does this sort of, well, because like in real life when we're trying to encrypt a message, it's either just alphabetical or let's say numeric, right? So I don't think any of those are necessarily prime numbers. So if we add, like let's say if we use this encryption scheme and we add more letters to it, does it increase like vulnerability in terms of like it's easy to observe like dummy letters?
yeah. I mean, actually, if you do not use the prime number, it will be able to be actually defactorized, and it becomes a easy problem.
But this still can be like decrypted by a malicious actor, right?
Actually, yeah, this is still can be decrypted pretty, because it's like the generator G19 is kind of very small, definitely. So, but actually, if the generator 19 is really big, then actually it will be it'll start to be more difficult. Yeah. So this is how we can increase the security and the difficulty. Okay.
I just have a question. Previous, like, even previous. Can you explain me the difference between, not the difference, but just like, can you help me explain that generator and like,
Generator.
so G to the power x is just like a multiplicative group.
Mm-hmm.
And what would be the additive group then, like if we had to like transform it?
Additive group is actually when you try to define the binary operation or Caesar cipher. Actually, in this case, we are having some mapping first, and then like having a g to the something, g to the x, and then using that we run some multiplication in the integer field, and then actually we map the result into the alphabet. So we have some processes. Yeah. So yeah, actually we are seeing that we are designing map here. We are designing our own map. So we have some elements, and designing and defining binary operation is actually what we are doing. And actually we are checking, okay, what kind of characteristics of this new designed operation actually looks like. Yeah.
Thank you.
This is the abstract, so this is the abstract algebra. So we are designing some mathematics for our own. And here comes a new concept, the generator. And in this case, when we try to define the multiplicative group, there exists some special element generator. So once for some of a element in that group can actually should make all the elements of the group. So for example, in this case, generators for additive group G actually satisfy a scalar multiplication. Actually, each scalar multiplication should be able to express all the elements of the group. Shall we? Maybe let's try to say we have a group with a 1, 2, 3, 4, 5. Then actually 1 plus 1 equals 2, and 2 plus 1, 3, 3 plus 1, 4, 4 plus 1, 5, 5 plus 1. Actually, let's say that we are modularizing it, so it becomes 1 again. And then let's 1 plus 2 and 2 plus 2. So in additive group, actually any of these elements can be some kind of a generator in this case. And what about the multiplication group? For example, let's say we pick a 1 as a generator, and actually it returns only 1. So it can be the generator. What if, like, if we choose 2, and to the 1, to the 2, to the 3, 4, 5, actually it will, if you modularize that, actually it will express all the elements of this 1, 2, 3, 4, 5. Then actually we can say that, okay, 2 can be a generator of this group, for example. So in the multiplicative group, some of the elements can be generator, and some of the elements cannot be generator. And then there is some algorithm to pick some effective generators, and it's mostly really using the powers of 2. So for example, powers of a 17 minus powers 40 like this. Yeah. Okay.
N is the set of integers, right? N.
And
Yeah. Is it always the whole set of integers, or will there be?
actually, it should be interpreted as a how many times you repeated the operation.
Does it have to be prime or
G and
both? Like what?
N is actually N can be done, from 1 to the size of the group.
Oh, okay.
And G actually there is a maybe generator without, which is not a prime. And G is just an element of a group. So yeah.
I have a question regarding additive group. Let's say if I choose 2 as a generator element, technically the resulting group is not going to be a group with all integer, but a group with all even numbers, right? If it's using 2.
True.
Yeah.
Right.
Yeah.
I'm sorry. Yeah. True. So because it's a repeat, and it's a repetition of a the operations.
So for
Oh. No, actually, because we are modularizing with 5. So actually, it'll come on the.
oh yeah, it will repeat. Yes.
The
Because it's
answer will be
modularizing.
the
Yes,
same,
yes.
right? Even if we
Yeah.
increase the count.
Yeah,
Not
because it
two.
will circle back.
Yeah.
Yeah, you're right. Got it. Yeah.
So actually, there are some interesting characteristics of how to pick the generator or something, but yeah. The only thing we need to remember here that generator should be able to express all the elements of the group. Yeah. Okay. Then this is the most famous kind of a group. Why actually we are defining the set of all integers, and then if you modularize that with a prime number, then actually it becomes a actually it shows a pretty interesting characteristic. What happens? Actually, we have seen a little bit here. What's the characteristic? Do you think? Actually, we already seen it in the Caesar cipher. Yeah.
The answer is inside the group.
Right. So it's a actually we can make it as a cyclic group. So we can make it finite. We can limit the number of the size of the group, and we can make it cyclic.
So like the answer will be random but still inside the group.
Right. Still inside the group.
So there is a bit of predictability, but there is not a bit of predictability. So there is a predictability aspect to it, but not really, like you cannot guess it.
Yeah, we say it becomes difficult. It becomes difficult. Okay. Actually, we covered all the important characteristics of the operation we are defining. So it should be a little bit difficult to know from the operation, from the result to the actually what the
Yeah, so the end is very hard to find.
right. But we should be able to compute the result easily. But if we want that, actually, what kind of element we are adding or multiplying inside of it, and it should be cyclic and have a finite size. And this is all the important characteristics we want to cover. Let's see, just move this.
So in this case, which is both G and Q the secret key, or actually Q is public, right?
Q is public, G is public. And we actually, let's see the Caesar cipher again. In this case, what do you think about the private key here? We can see this case first.
There's a K.
What's the private key?
Yeah.
I think for the additive one, it's the shift, right? The shift is the private key, right?
Shift is
Like how much shift, like how many letters you are moving forward or backwards. I think that's the private key.
It's a generator.
Oh yeah. Oh.
It's the generator. So when you think about that, the first one, what do you think the first one? It's pretty easy, right? It's a yeah, it's a hello world.
Oh.
It's easy, right? And yeah, maybe okay, we can just, if you know the generator in this case, actually it's really easy to decrypt it, right? And what happens the second one? I'm gonna give you the generator, but it's really difficult to know actually what it is,
Yes.
right?
Yeah.
Then actually, what's the thing that we want to keep here as a secret? The plain text, actually, hello world,
Yeah.
or right?
Yeah.
So it's something like G to the H, G to the E, G to the L, G to the L is something like that. I mean, so we are actually trying to hide what actually it's in the power for the generator. So it's yeah. And this is actually called the discrete logarithm problem. Because if you define that y actually equals to g to the power of x and modularize that with prime number p, then actually it is difficult to know that using y, actually actually what is X there. So this is called the discrete logarithm problem. And the reason why you were difficult to decrypt the multiplicative version of Caesar cipher was because of this discrete logarithm problem. If it is easy, then actually our whole encryption will be broken. Yeah.
CC will be okay.
So, in the first definition of the multiplicative group with Caesar cipher, there's also the K. So even that can be public, right? Well, actually, it's not
Actually,
necessary.
K.
Because it's constant multiplication. So
Yeah, it's a constant multiplication.
is it more like a non-zero line?
Yeah. Actually, let's see it. Just a moment, please. Actually, it's been a while that I made this slide, so I can't remember exactly what was K there.
I think K, in this case, K is technically the generator. Because in this case, we take GA times GK, right? G to the power times G to the power K. So G to the power K is technically the generator, but to find out what K is harder than adding and addition, right? Because you need to multiply. And depending on how many times you multiply times a certain amount of K, it's hard to find like what K is, I guess. Is it? Because there's a slide that says GA times GK.
Yep.
Yeah.
So let's go to the definition again.
Yeah.
Yeah. Right.
I think we have to go back one more
There's
slide.
one more slide.
Yeah. Yeah. GA times GK.
Yeah.
Yeah. So GK is the generator, I suppose.
No, G is the generator.
Sorry, yeah.
Yeah. Three is the generator.
It's like a song.
Yeah, I mean,
It's like a song,
Yeah,
right?
it's a
It
song.
difference and other permutation.
yeah.
It can be other things as well, but it's I think like very abstract.
Yeah. But actually, I think that it has a little bit of an error inside this example to exactly explain the multiplicative group with the Caesar cipher case. But I think the purpose of this thing is just getting a sense of what is the discrete logarithm and getting a sense of what is the multiplicative group. And maybe I think we need to define and design it in a much more some exact way. But yeah, it was kind of experimentally. I just tried to define Caesar cipher, the multiplicative version of Caesar cipher. So yeah, we need to polish it a little bit more.
It still works. It's still very hard to find what K is actually. Yeah. Okay, Martin, maybe you can try to brute force it, but it's still harder than additive one.
P and Q is one of the problem. So that's K of the
Okay, then now it's a time to go to the next part, the cryptography. Yeah. Everything is actually just for the abstract algebra, the introduction of the group. How is it? Are you all actually can explain what is group? Okay.
Let's ask questions. If you have asked them, you will get a chance later, right?
Okay. Then we're gonna try to define another group, and there is an elliptic curve point on the group actually we are trying to define here. So to define an elliptic curve, we need to know a little bit more about another concept field. It's also just similar to how to define group, but field has a little bit more some characteristic compared to group that we call that if it has the binary operation is a commutativity, we call that as a commutative group or abelian group, and field is an abelian group. So if actually Caesar cipher, I think Caesar cipher is a abelian group. I think it's because we anyway define it in addition multiplication, so it should be commutative. So field is actually usually denoted as a bold F, and these actually should be defined with two different binary operations. And we usually say that one is we usually denote that one as a addition, and the other one is a multiplication. So field has two characteristics. One is a abelian group for addition, and another one is a abelian group for non-zero element for multiplication. And then if that, we should be able to define the distributive law there using the addition and multiplication, which means if we have some points of the elliptic curve, then we should be able to add those 2 points. What does that mean? We're gonna have another new point. And also we should be able to multiply, actually points, elliptic points are not the field. So if the elliptic points are the field, then if we multiply 2 points, then we're gonna have another point. That is the how we define the field is. But don't be confused that elliptic points are not field. Okay. Yeah, I think we can just try to go to the how to define the addition of an elliptic curve point. Okay. Before we go that, actually, the reason why I explained the field is that we should define the elliptic curve on the field. Yeah. So, which means that elliptic curve means you have a x-axis and y-axis, and x-axis and y-axis actually are field. So, okay. We're gonna visit some page here, but okay. It doesn't work. Let me just type it. I think this website is a kind of provides the best introduction regarding to the elliptic curve cryptography. So in this elliptic curve cryptography, we are defining the addition in a geometric method. So this is how the elliptic curve looks like. And then if there exist 2 points P and Q, then actually we are defining that the result of the P plus Q as actually where the intersected point and reverse it to the y-axis. Because we love to say, we love to write like P plus Q plus R should always will be 0, and then we can move it to the right hand side, then P plus Q it becomes defines R, and then we are saying that P and Q and R on the same line. So we are just defining then a geometric approach. So here are 2 points, and what we need to do is finding the intersection point here, and then reverse it is how to get the result of the addition of the 2 points. Then let's try to find the point by ourselves. So let's say we have this current in P, and is here, and Q is here. And then let's say P, actually it's X is X of P, and like this, and Q. Looks like this. Then we have the standard form of this graph, which is this correct? Maybe.
Yes.
Yeah.
Yep.
Okay.
X
Everyone
squared.
knows. X squared.
No.
X squared. And X squared.
Okay, good.
No, I think this.
No, no, no.
It's correct.
I think yeah.
Right?
Right.
Yeah, we can check it. But then actually, how can we find this intersection? Just simply, we are actually defining a line here. For example, like y equals plus something. K, yeah. And then we can just compute this m and k, and then putting it here again, and we can compute the result, resulting x. And then we can also compute the y here. Then we're gonna have a xq and yq. Then we just reverse the y-axis. This is how we can compute the resulting point. Okay. So we actually define a new set that we are trying to think as a number. So this point is corresponding to a number in our head, and we actually define a new addition operation using this geometric approach. Then why actually it will introduce us something similar to this logarithm problem. Actually, the reason why we are doing this is just to make it difficult, right? Let's see actually what happens here. Let's see. So this website also provides us a visualization tool. Yeah. So we have a P and Q and R here. Then actually we can define another some interesting stuff, which is called scalar multiplication. It's something like it says how many times you did the addition. So let's say P plus P, and it's 2P, and the scalar here is 2. P plus P plus plus P will be kind of n times P. And then actually our mission is that, okay, if we have this scalar multiplication, our mission is that, okay, it's letting it be difficult to know actually what is n here. This is our mission. Okay. And let's see actually what happens in this visual tool, that we are actually defining the addition in the real number field, and then yeah, we can, let's see how the multiplication will look like. So I'm gonna increase the number here in 1. Actually actually should equal to here Q. And 2 actually means P plus P goes to Q. And 3 is P plus P plus P, and like this. But you know, it'll be it's in the real number, so it's not discrete. So it has an infinite number size. The size is infinite, and if we define that on the field, if we define this curve on the field, let's see actually what happens here. So we have a discrete number of elements here. So here, let's see what is the this curve. It says this curve has 100 points. 100 points. And then let's try to add. Here's a 1p is q. For example, let's pick another number here. 20. Yeah. So it becomes a little bit difficult to see the pattern here, but let's try to see how the multiplication works. Then here we choose p as 3.6 here. Here's where the p is, and then if you multiply by 1, it should be equal to p, and multiply by 2, it becomes like 80, 10. Let's go 3, 4, 5, 6, 7. Do you see some pattern here? Okay. Right? Repeating. Yeah. So actually, this is how we construct a subgroup. Because you know, you can see here that how many points we have here. 100. And how large the size of the subgroup we try to make here?
4 or 5.
It was 5.
5.
Yeah. So do you have any hint here?
Some model.
Yeah. The subgroup actually it's the size of subgroup is actually becomes a factor of its kind of a model group. Yeah. So in this case, actually, for us, it will be difficult to use the group with these 100 points because we're gonna have 5 different answers, right? I know, not 5. We're gonna have 20 different answers, right? It's repeating, right? So because of that, to make it more usable, what is the easiest way? Make it the order to a prime. Then we can use that just directly. I mean, let's try to define another thing. What it is, for example, 3. The generator has 96 points here. 5, 4. Okay, this has 90 points. 5, 91 points. It will have no subgroup. Right? And then we can use it directly. And you can see that this is actually defined in the field, in a prime field where P is 97, but the number of the electrical points here is 91. Both are prime, and this is actually, if you try to build something for a zero knowledge thing, then you may encounter there exists an FQ, FR, etc. Right? So basically, FQ is used for generally the the prime of the field. And R is used for the size of this group. Both are prime. So in this case, R becomes 91 and Q becomes 97 because this electric curve is defined on a prime field where prime is 97 and actually it has 91 points. So if we actually I share that our mission is that making it hard to find this scalar from some different points. Then in this case, this scalar, it belongs to 0 to 90, right? So you're gonna have a 91 point, and the scalar, the range of the scalar is from 0 to 90.
For this case, from what I understand, looking at definition of elliptic curves, for example, like each different type of curves that you define. For example, the SECP 256K one, they have a certain set of parameters which fits into this curve formula or curve polynomials and result of this. That also includes the generator. Does the generator affect the size of the group created?
Actually it depends on. So there are different types of elliptic curves, and actually we sometimes intentionally using subgroups. Yeah. Because some of a subgroup can be interpreted into a much simpler form of elliptic curve, and we're gonna cover that a little bit. Yeah.
Why do we use subgroup?
Because if we define a elliptic curve with this standard form, and then actually sometimes it has a subgroup, and then if we use the subgroup, then we can convert the points into a corresponding another easier form of another elliptic curve. And actually it makes us much easier to compute the additions or scalar multiplications. Yeah. Because let's say that how do we compute this n times p in a easier manner? For example, we have let's say this p is a generator, let's say G. We have a generator, it's an elliptic curve point, and we are doing a scalar multiplication. And doing kind of a 10 times of G might be pretty easy. But what happens, this n is actually a really big number, it's going to the 3 in 2053 bits. Then how can you do that? We cannot do that like just to 253 times, right? So actually we are doing some double and add approach, because yeah, let's say double and add is something like this. So let's say 10, it's 1010 in a binary form. Okay. And like close. Right? For example. Yeah. And then actually we can do 10 times of G in a way that I'm gonna add G, and G plus G becomes 2G, and then 2G plus 2G becomes 4G, and 4G plus 4G becomes 8G, right? And this is a 8G, and this is a 2G, 2G, 1G. Yeah, this is how we do the double and add. Then, in case of 253, actually, if we just repeat this 253 times, then we can compute the result without doing this 2 to 253 times. Yeah. This is how we do the double-ended problem. So this is pretty effective, but actually there might be another some more efficient way to compute these things. So this is one of the most representative algorithm to compute the scalar multiplication of the generator, and actually it is important for the performance wise.
Yeah, but like, how does this matter with subgroup again? Like,
Subgroup?
Yeah.
Actually, we're gonna cover that with the Edward type curve.
Just want to make sure, right? So we have few, right? Like the tram, like 97, right? And then we have the 91 points, right? And then for subgroup, we just select differentiator that can have the number of elements in group that is like can divide the whole points, right? Let's say the number of elements in subgroup will be able to divide the big things, right?
Because it's
So yeah, and so basically like the security of subgroup will be slower than the elements
because it's anyway it's a factor of the order of the say model.
Yeah, so it will be lower security, but then we get what again, like from using subgroup we get the efficiency. We will cover.
Yeah, right.
Yeah, I was going to one. Like, I had the same one.
I was gonna quickly ask whether the size of the subgroup only depends on the generator or also depends on A and B.
Generator and A, because A and B will decide actually the number of the curve points, and also the field
I see.
where the curve is divided.
Every generator needs to be on the curve anyway, like we can pick different one to start from. Like every generator that we use as a subgroup generator that needs to be on the curve anyway, but we just pick it.
Yeah. Every generator should actually definitely be able to express all the elements. And then the subgroup generator will express only the subgroup elements.
Okay, but yeah, the subgroup operator is still one of the
One of them,
yeah.
Okay, because it's a subgroup. Yeah. Okay.
Quick question.
Yep.
You mentioned that that's algo that's faster than like double F, right?
It's a double-ended.
No. Did you say that there's another way that's faster than this or no?
There is a faster way.
What it's called?
So
So I think you know.
I'm sorry, there's not an alternative of the double-ended, but actually that's a way to exactly compute this addition. It's all.
Okay.
Okay. So let's try to see that it's really difficult to know here. We have a Q here, and actually if you don't see this number, then from this P and Q, can you imagine actually what the N here is? It's pretty difficult. Yeah. So it is called the elliptic curve discrete logarithm assumption. That we are assuming that this is difficult to solve, but using quantum algorithm, it will be easy to solve what the N is here. So it's called this elliptic curve discrete logarithm assumption. It's not a logarithm, but actually this definition of discrete logarithm problem started from the multiplicative group. We are trying to make a pretty similar thing with the scalar multiplication using the addition in the additive group. Actually, it should work in the same way when we use the multiplicative group. So in multiplicative group, it's difficult to know what the exact power from the result. And in this additive group, it should be difficult to know the scalar multiplication, scalar from the output. So it's kind of so sometimes if we have generator G, the discrete logarithm assumption is actually G to the X, but in our case, we are using the X times G. And actually they are expressing the equivalent problem that it's difficult to know this X here when we have these generators. So sometimes people just use this notation, and sometimes people use this notation.
But do they mean the same thing? Or like,
Technically and theoretically, they are different, but they have the same characteristics. So when you just write this multiplicative form, many of them just can be rewritten in this additive form. I'm gonna actually cover what's the difference in the parent.
Yeah, so the G to the X is just multiply, well, quote unquote, multiplying 2 points, right? Instead of, okay, got it.
Yeah. So, but actually inside of it, we're gonna like express, this is multiplication, and xg plus yg is an addition, and you're gonna be like this. Yeah. A little bit different, but works pretty similar.
Which one is easier to compute?
Which one is easier to compute? I think
To find easier.
yeah. Addition is definitely much easier. Because we can think like addition is free. Always scalar addition is free, but scalar multiplication is not free. It's an expensive computation. Okay, then we have covered pretty much. And then we're gonna see actually where we can use this characteristic. The elliptic curve discrete logarithm assumption. Let's go back to the slide. Okay. I just explained that with the whiteboard. Also explain the double net, yeah. And so the basic case is the Diffie-Hellman key exchange. So if we use the discrete logarithm assumption, Diffie-Hellman can be expressed like, okay, we have a element A, which is a g to the small a, and also an element B, which is g to the small b. And we're gonna use that large A, capital A as a public key, and small a as a private key. Does it make sense? Because it is difficult to know the small a from large A. If you have the discrete logarithm problem, right? Then we can use large A as a public key, and then we're gonna make it's basically what we are using when we use the HTTPS. So we have a server, and I have my own client, and I would love to access to the server and communicate with the server. And then we're gonna make a secret key that we can share with each other, only the server and my client. So server will have a public key large A, which is the TLS, and then yeah, Chris, okay, and B, okay, B is my client's public key. Then the shared key will be something like this: G to the AB. Then a third party when come, maybe can he know actually what the G to the AB here is? I think because to know that, some of you need a small a or small b, right? So server A, actually if the server has a small a, then server can create a shared key by the multiplying the small a to the client's public key. And the client can do that vice versa. So they know, the two parties, if they know each other, the shared key there. So this is how the diffie-Hellman exchange works. And basically this is how we are generally expressing in the multiplicative form. But we can do the same thing exactly in the additive form too.
Can you explain me again? I didn't get it.
Okay. Yeah, let's say when come? Can you come here? Yeah, sure. Would you please pick your some private key, small number,
Small number.
Yeah.
Private key.
Yeah.
3, 5.
5. Yeah. And okay, let's say the generator is a 17 here. And 17 is that too big? Like 3. Let's say generator is 3. Let's say 3. Okay. Can you please compute your public key? Yeah, let's get some help.
253.
253. Thank you.
Okay, thank you.
253. Okay. Public key, right?
Yeah.
253.
Is your public key,
Yeah.
right? Okay. And I'm gonna pick and let's say I'm gonna pick
243.
Oh, sorry.
I'm gonna pick 7 for my private key. And then say 243. Yeah, say my public key will be like but you know, let's try to, this is not some right case, but we can actually modularize that. But anyway, let's say this is my public key and this is Wenkan's public key. And then we're gonna actually communicate with each other. So we're gonna create a shared key with Wenkan and me. And yeah, would you please compute your shared key here?
My shared key.
Yeah,
Oh my
your
God.
shared
It's
key.
becoming big.
It's
Yeah.
coming big. 2, 4, 3.
Is this-
G8 times?
But
I
no,
think
no,
it's
you're
yours.
taking his public key. He doesn't know your private key.
Oh, yeah.
So how is
You
he
have to
going to
raise
come
it.
to
Yeah, so
his
we
shared key?
His.
He doesn't know
and
my
then to
private
the
key.
power of 5.
Yes.
Oh, this is getting very huge.
Yeah, actually, yeah, this should be enough. Yeah, we don't need the exact number.
Okay,
This
okay.
should be enough.
Okay. Oh.
Okay.
Yeah.
And okay, Wenkan, thank you so much. I'm gonna compute my shared key too.
Okay.
What is your public? Okay, your public key 243. And then I'm gonna I know your public key and I know my secret key, but I'm gonna actually exponentiate that with my secret key. So let's compare that actually. They are equivalent to each other. This is actually how we do the diffie-Hellman key exchange. Good?
Yep.
So with this shared key, am I able to reveal
Wenkan, yes.
Wenkan's public key.
private key?
We don't need to, actually Wenkan will never reveal his private key here. Because this is Wenkan's private key. And this is what only Wenkan knows. And I actually shared my public key. And to compute the shared key, Wenkan used my Wanseob's public key and use Wenkan's private key.
Oh, okay.
And I am using Wenkan's public key
Public key
and I am using my private key.
I got it.
You result in the same shared key.
Yeah, and then the result will be the same. And because actually any of you doesn't know the private keys of Wenkan and mine, so you might not be able to get the same shared key here.
Unless you know what one subscriber key is.
Right,
Yeah.
or yours.
Yeah, all mine.
Yeah.
Oh, you know mine now.
Great. So this is the difficult and actually we can do the same thing using the additive and scalar multiplication for it. Because let's say yeah.
But for the ECDH, the efficiency and the computation will be much smaller than for the difficult and
Yeah, usually actually this is much efficient compared to these multiplications.
But the security is still the same.
Security?
This one's more secure.
This is smaller and with the same security. I mean, yeah, if it has the same size, the security of this addition multiplication will be much better. Actually, not much better. Not much better. I'm just referring the security model of the RSA and the ECDSA, but actually this is not a exact comparison here.
I think it's
just
like
computationally.
Yeah, it's cheaper to compute, but I think it's
Right.
so to say a little bit more secure because EC we usually work with modular group, so it's hard to predict where it will go to. Whereas this has a almost an infinite size. I
Right.
guess. Yeah.
Okay.
Yeah, no problem.
Okay. Yeah, and actually we have another examples like encryptions, but actually I don't think we need to cover this to understand how the cryptography works too much, because Diffie-Hellman is the most simplest example, and let's think about the signature here. The Schnorr signature is the easiest form of the elliptic curve signature stuff, and ECDSA is a tweaking a little bit, so we need to write a little bit more equations to understand how the ECDSA works. But I think the Schnorr signature is pretty enough to understand how the elliptic curve signature works. So in this case, we have some parameters. We have private key small k, and then the public key is large P. So K times G will become the public key P here. And then I'm gonna sign a message using my private key. So here I will say the challenge is small e, which is kind of a hash of the messages, for example. And then making it as a modularized with the size of the scalar order of this group, of these elliptic curve groups. Then let's try to make the signature using E times K, because I am the only person that I know the K, small k, so maybe I might be the only one who can make the signature E times K, right? And let's see what happens there. You share your signature, then people know the challenge. So dividing will give you the private key problem, right? And how can we prevent this problem? Maybe we can try to add some salt, right? So we are adding choose a random nonce small r here, and then we're gonna share this signature and add some salt to this signature. Then the signature will be something like ke plus random salt r, and then to verify that signature is valid, people should know the verifier should also be aware of the information of nonce in a different form. If you share the nonce, or you can just subtract and then you're gonna get the private key. So we're gonna give the nonce in a public form with the electrical point. That will become the large R, which is a R times of a general energy. And then you are sharing your signature with small s and signature and public nonce. Maybe we can actually easily verify that, right? I mean, yeah, can we verify that?
Yes.
Can we verify that?
Verify the signatures, right?
Verify that the signature is from the public key P. Can you verify that?
Yes, you just have to compare, take the big R and then add it to the
Public nonce.
yeah.
Right. So this is already you have this information as, and you're gonna actually multiply generator with this s, and the result should equal to R times G plus KEG, and you know KG, the public key, and you know challenge, right? And you know the public key. Shall we write down?
Yes.
Okay. Right now you gave me the you can just sit down. Wenkan gave me the signature S, and also Wenkan's public nonce was R. And then I'm gonna check that. Actually, Wenkan signed using Schooner's signature regarding to a some challenge E. Let's say E is a hash of the transaction, for example. And then I'm gonna check that Wenkan's signature is valid for this challenge E. How to verify? I'm gonna multiply with to the generator with the scalar s, and then actually it should equal to, okay, Wenkan, actually you already showed your public key P.
Yes.
P plus R. Because public key times challenge plus R. Because actually this signature should be a nonce plus challenge times Wenkan's own private key. Then it will be like this. E times KG. And actually this is actually the public key. And this is actually the public nonce.
Oh, okay. And
Right.
R times K times G is also equals to RG times KG. And RG is the big R.
So checking this should be enough to check Wenkan's signature is valid for this challenge E. This is the simplest form of a electrical signature. Okay. Okay, now I think it's a time to go to the breakout sessions. Okay. I'm gonna share the link for this slide, and then let's try to skim through the concept, and let's try to explain with each other there, and let's see that we are actually understanding all of these concepts. And if you have any questions, then we're gonna Wenkan and me just hopping around, and we'll help you understand.
We need anything else? Any other piece of information that's not in the equation? No, that's it. That's it. Okay. So we need to figure out the equation.
Yeah.
Yeah. So, okay.
Yeah, it's very simple.
Still got like some random addresses. Yeah.
Yeah.
So we need to find a line.
Yes. We should.
How much is 0.0?
$5 each.
It's just too small, but
Some OPs are smart,
say,
not
yeah,
reasonable.
one cup of coffee for each.
Hey, coffee is coffee.
Okay. Okay, thank you everyone for following up. Let's actually, I think the part 2 is the most the boring part of the all of the things for the 3 days. But yeah, it will be a kind of foundational analysis to go through the other things. And actually, around from 3 p.m., we're gonna have a really fun thing from there. To do that, we need to understand actually how the electrical cryptography works in a little bit more detail. So, let's go. So, yeah. Maybe, I think we've already covered this in the breakout groups. So, is there anyone who can try to explain that? Yeah, maybe each group can send one person for each question there.
So group 1, who's the group 1?
Group 1 explains the group.
Yeah, group 1. Don't need to be shy, everyone. We just go quick.
Okay.
The other groups as well, just send one people up. Wherever you are, I just got call up, you're out.
Okay. Here's the markers.
By the way,
Come on, one.
the notes you have is over there. You just have to come up here, talk about your notes. You can come up together as a group if you want to. Yeah.
All together, you can come all together.
Yeah, why doesn't everyone in the group come? So who's in group 1?
Group one, come.
Group 1.
Give a raise your hands.
Guys, yeah.
Yeah, we are group 1.
You have forgotten your group?
So,
He's trying to get the
I already got it.
Oh, nice.
Really, I
Really got it?
Let's see.
Let's see. Okay.
Down.
Yeah. Actually, I brought some food from Korea. So
Oh.
please let me give you the as a gift. I'm gonna bring that tomorrow.
Oh, yeah. Thank you so much.
Okay. And anyway, before we start to talk about the group, maybe can you please explain what you have done? You tried that?
Yeah, sure.
Yes, please. Please. Let's try.
ChatGPT. It's mostly that,
Yeah,
but
please explain.
I kind of know the process. Yeah.
And please explain.
Yeah, sure. One second.
ZK.
ZK.
Some ZK. Okay.
Yeah.
ZK so.
Yeah, ZK is on ZK.
Wait, did someone already train it?
Yeah.
He was highly incentivized.
Yeah, so let me start with the maybe with the text first.
We have a lot of coffee now.
Yeah. So the cipher text, to decrypt the cipher text, we need to do Caesar shift, Caesar cipher with a shift of 7. So if we know what the text is talking about, and the text gives an instruction that's saying that we need to find a polynomial that has degree 6. So the first step we need to do is find a polynomial. Maybe a degree 6 polynomial. Yeah, so with degree 6. Then once we got that, we have to evaluate it. The polynomial with 9. Value 9. So once we've done that, we need to take the result to result to and do modular arithmetic, like modularize it with finite field of baby Jacob. Yeah, so that's it. That's how you get the private key.
So the x and y is for the polynomial.
But there's some steps in the first and second step. Yeah. So x and y is the point that used to find the polynomial. Yeah. So we are given with 1 point from the QR code, right? Or maybe before that we need to explain how do we actually find the polynomial. So to do that, we have one method called Lagrange interpolation. Maybe not here. Lagrange yeah. And to do that, you need like at least multiple points of maybe at least 3 or more to get an accurate result. But we only given 1 point. But if you not notice this, everyone actually given different point. So you need to collect like yeah.
Oh,
Yeah, so every QR has different yeah.
How did you collect that?
Do you still
Like QR codes for them.
Did someone put the QR codes on the table?
In fact, it actually found out by Nazrin. Yeah, so yeah, my friend sit beside me, and then we just yeah, and then we just search around. Like there's a lot of different QR codes.
Social engineering, this one.
Yeah.
Try together with some friends.
How to hack.
Yeah, and I asked GPT how to do it. It says I need to at least 7 points to find a degree 6 polynomial. So I need at 7 points. So once I gather that, so all of the puzzle pieces have been collected, and I just with the help of AI GPT to help me calculate the result. And yeah, so by going through all this process, I received one just integer, a very long integer, and convert it to text value, and that's the private key.
Yes.
That's the private key.
Question. Actually, maybe when you were doing the Lagrange interpolation, actually the value might be too big to be handled inside of your computer.
Yeah.
Maybe ChatGPT did that instead of you.
Yeah,
How
I
can
think
we do that? Because it's a really a big number. So it's a kind of this field was kind of a 254-bit size.
Yeah.
So it's kind of degree 6. So the number is something kind of a 100,200 like ish big number. This is something cannot be computed inside a computer. How did you do that?
No, he didn't. Yeah, he gave the answer, but he did not tell me how to do it. How should I actually do that? So yeah. No, I didn't calculate, but he can do that. Maybe he has already some data around that, that's why.
Thank you so much. We're gonna visit how we can handle this kind of big numbers inside of computer later. After we actually recall the concepts we have visited in the morning. So group 1. Okay. Yeah. And then could you please explain what the group is?
What is group, right? So the group is a set of elements that follow certain rules in simple terms. And these rules are photos, closure, associativity, identity element, and inverse element. Yeah.
Yeah, it's pretty simple, right?
Yeah, and should I explain what is this for?
Yes, please.
Okay. The closure is product of any two elements of the set will be in the set itself. For example, if we get the set of, let's say, numbers, integers, and 2 and 3, if they're a set, the product of them will be 5, so it is also in the set. That's closure.
Yep.
Okay, associativity is order doesn't matter, in simple terms. For example, if we add 2 plus 3 is 5, 3 plus 2 is also 5. Is it?
No, associative should be like, let's say you have 3 numbers. It doesn't matter whether you do operation on the first 2 numbers first or
It's related to the order.
Oh yeah,
Yeah,
the operation.
Yeah, still related to order.
Sure. Sorry. Identity element is okay. Operation with identity element will result in the element itself. That's identity element. For example, if you are addition, it's 0. You add 0, it will be the element itself. If it's multiplication, it's 1. Multiplied 1, it will be the element itself. Inverse element, okay, it's an element that can undo the operation you did, in simple terms.
Yep.
Is it a good explanation? For example, if we shift in the ciphertext, in the Caesar cipher, by 4, if that was an operation, and the inverse element will be minus 4 to undo it back. Yeah.
Great.
That's it.
Yeah. Technically, the inverse should output the identity always.
Identity.
Yeah. So for the additions, identity is 0. So for addition, the inverse of 4 should be minus 4 because it returns 0. For multiplication, the identity is 1, and the inverse is kind of a divisor, like 4, then say 0.25 is the inverse in the real number.
Oh, okay.
Great.
Yeah.
Yeah. Then group 2, can you explain what the
That was
field?
easy for the
the
game. that was the thing only did. First one was the easiest.
Just come on. Come on, please. Don't be shy. Don't be shy. Okay.
Okay. So basically, field is a set of numbers. So the numbers will contain the original set of number, and then they will also have the multiplicative inverse of the numbers. So if they only have the numbers like 1, 2, 3, 4, and they do not contain their multiplier inverse, which is like 1, the multiplier inverse of 1 is, the multiplier inverse of 2 is going to be a quarter, which is 2 over 1. So if it doesn't contain, it's going to be a ring. And then if it contains it, it's going to be a field. So basically what the field has, it has 2 binary operations. First one is going to be addition, and the second one is going to be multiplication. And then normally if it's for multiplication, it's not going to be 0. It's not going to contain 0. And then one of the things we're going to have is called the abelian group. So abelian group means that if it's two elements A to B, A to B is going to be B to A. That's going to be the definition for an abelian group. So for all fields, all of them are going to be in the abelian group. And then the other thing is there's something called a distributive law. So A, as an example, the elements A, B, C. When A times B plus C, when B plus C is bracket, so it can be broken down into A times B plus A times C. That's going to be the distributive law for B. That's basically what I understand.
Great, thank you so much. And because we now have this field, actually there was a main reason why we could use Lagrange interpolation in an easier way with the field. Because if we just did the computation in the real number and then actually modularize that with this prime at the end of the computation, actually it's too big. So we can do all the computations in the field. That is actually how the Lagrange interpolation can be conducted in a much cheaper way, because we modularize every time, so the intermediate result will be close in the field. So we are not actually handling a too big number there.
And we can do the same thing with like squaring and then modding before we do it multiple times.
Yeah, right. So basically, if you have some arithmetizations, actually it consists of additions and multiplications. Actually, the result always should be same if we just do the same thing in the field. Yeah. Great, thank you. And then group 3. Very good. Yep. Scalar multiplication of BCC, please.
Anyone? I don't think I have the paper. Oh, it's okay. Maybe we can just try to give a general explanation. You want to go for the Scala?
Scala, yeah. Okay.
Okay. Scala
So that's the short added.
Yeah. So I guess the understanding of Scala multiplication of elliptic curve is that on the elliptic curve you have a set of points. So when you are doing Scala multiplication on, let's say one of the points on the curve is you are just doing repeated addition on the point, let's say. So when you are doing addition on the point, the result of doing that addition is you will generate another point that is on the curve as well. So if you do this a lot of times, and if the scalar value is very large, and then it becomes hard for anyone to know what's the scalar value just by looking at the output of the addition or of the scalar multiplication. So in the context of like public and private key cryptography, the private key would be the scalar value, and the public key would be the result of the scalar multiplication of the integers, which is the public key. So
yeah, then would you please go through the exhilarating system
my understanding is that, yeah, like I mentioned, because if let's say if you only look at the output of the scalar multiplication, which you are looking at just a point on the curve. If you want to know the secret value, which is the scalar value, it's not possible to do it. You can brute force it, but if n is very large, then it wouldn't be feasible. So I guess that's why that's his previous assumption. Yeah, from my understanding. Right? Any else?
No. we didn't really discuss these two questions just now, to be honest with you.
Okay, thank you so much. And group 4, can you go through the how to create a shared secret key using ECDH? Group 4?
Oh, very good.
Yeah. Good.
Outstanding.
Yeah. I've seen the team.
In support, yeah.
It's a team.
When you review the topic.
Yeah, actually, yeah. Oh.
Okay, so for creating a shared key, we will need first A, which is the public key. I'll just write it public is equals to the generator G to the power A, where A is the private key of the byte A. Same for B, public is G to the power B, which is same private key here. And to have a shared key K, we'll
What about the ECDH?
How about the ECDH? We have the generator-big G.
It depends on.
It depends on the first, the previous two questions. So, in going back to what group 3 said, the scalar is essentially the secret, right? So now basically then we, instead of having GA, we have A multiplied by the generator, and then B multiplied by the generator. So in this case is A G.
Perfect. So we have a really good sense of the why we are using elliptic curve for the discrete logarithm assumption. So we're gonna go a little bit deeper of the how the elliptic curve actually looks like. So it's a little bit boring, but actually after that we're gonna handle a really interesting topic after this. So this is the basic form, the bias transform y to the 2 equals x to the 3 plus ax plus b modularized p. It's a something kind of a, we are defining this elliptic curve on the field, on the Pliant field. And actually this polynomial, this elliptic curve actually satisfies the overall complex group load here. So just a moment please. It works, right? Good. Yeah, actually we simply talked about in the morning session. Actually it contains some rule. So abstract algebra is all about that we are designing our own rule. So in this case, we are actually defining the elements with this point, and we are defining the addition rule. But this bias transform actually has some edge cases. For example, what about P? Actually, what about this line does not meet any other points there? For example, actually the line can look like this, for example. It will never meet another point, right? So for those edge cases, actually we have a special rule for addition. So this is the limitation of the bias transform. So, yeah. Anyway, we're gonna take a look at the real use case, the SCP-256K1. The prime number P actually looks like that. So it's a 256 bits value, and the A is minus 0. And yeah, B equals 7. Actually, yeah. Okay, and actually we have a generator there, and the order of this elliptic curve is actually also the 256 bits. So the order and the prime field size is different. We all know that, right? So I think we don't have that elliptic curve. Not sure. But yeah. Not correct. Yeah.
And the second question, I guess, is does it matter whether P and N is about the same size? One is
Yeah,
very
it
big.
matters because mostly actually the order is pretty similar to the order of the P, and actually we're gonna handle that when we talk about the folding schemes inside. Yeah, because for example, let's say that we have a some elliptic things, and let's say the output has some order with n, and actually if the order is exactly same with the field size, then actually we can actually put them inside of the another thing. So we can make it something recursively prove something in the future. So actually in that point of view, the P and actually an order, the prime field and the order of the scalar actually matters. Yeah, and let me explain about the cofactor a little bit more. So let's say that we define a elliptic curve on a finite field. So we have, let's say we have actually a discrete 10 points, for example. And actually I try to pick a point here, let's say P. And 1P is this one, and 2P is this one, and actually 3P is this one, and 4P is this one, for example. These, if then, these 2 points actually consisting a subgroup with order of 2. So this subgroup's order is 2, but actually the order of this whole elliptic curve is 10. And the cofactor here is 5. I mean the size actually P and 2P actually is a subgroup of this bigger elliptic curve, and the order of this subgroup is 2, I mean the size, and order of this subgroup is 10, and cofactor here, H, is 5. And cofactor, when the cofactor equals to 1, it means that, okay, actually, it does not have any subgroup. I mean, right? Okay. And then, we have another curve, SCP-256R1.
Sorry, can I ask another
Yes, for sure.
question? So just to kind of recap what a subgroup is that you pick a generator where so for this example, right?
Yep.
That generator would just generate those 2 points, right?
Right. Right.
And then that makes a subgroup, right?
Yeah, right.
Oh.
This generator, P is only the generator of this subgroup because actually it outputs only these 2 points.
Okay.
But actually, for example, if we actually pick this elliptical point, and actually, oh, interestingly, actually we can express all the points with this one, for example. Yeah, then actually Q is the generator of this group. Yeah. So P is the generator of this subgroup, and Q is generator of this elliptical point.
But if the order is prime, then there is no such subgroup,
Yeah.
right?
So if the order of these points is prime, then actually we're gonna have a unique subgroup, which is exactly equivalent to this graph.
Yeah.
Yeah. So yeah. This is how the SCCP curve works, and we can change the number a little bit. So this is another curve with SCP-256R1, which is being used for Face ID, etc.
Are there any meaning in this naming convention like K1, R1?
Actually, I don't know about the naming convention for K1 and R1, but yeah. Maybe ChatGPT can help us. Yeah. So we have another prime P, and actually you can find that we are actually choosing a prime with a combination with the linear combination of the powers of 2 here. Because if we just make the prime number with the combination, linear combination of powers of 2, actually it has some good characteristics because we can express them in bitwise of like expression. And then, so how to pick the prime number is something like do some linear combinations and do some primality test, then checking it's prime or not. It's how to pick the number. And then we pick another A and B, and generator and order, and say cofactor is also 1. But as I actually it has some sort of a edge cases. Because of that, which means we need to define the actually flow control when we write some program. So when we try to implement this in programming, then let's say, okay, I'm gonna add point 1 and point 2, and then using the flow control, we're gonna check the conditions. Say, oh, is it in an edge case? Then actually use this algorithm. Is it in this case? Then actually we're gonna use this kind of some geometric approach, etc. Which means it's kind of a computing overhead. So in analytic curve, it is pretty important to have a simple rule instead of a kind of some complex design. So actually Montgomery curves actually help us doing a much simpler approach, because actually this can be converted to a Edward curves form, vice versa with each other. Which means here we need to see actually how the Edward curve looks like. Let's go here. This is how the Edward curve looks like. So let's try to think about only the first three terms. X squared plus y squared equals 1. What is that? Circle, right? And we are adding a one more term, which is a plus d x squared y squared. And then actually it will look like the right figure. It still actually looks like a circle, which means that we can use the Euler equation there. Yeah. Maybe should we remind the Euler equation? Okay. When we have circle, if we express circle in a complex plane, then with a unit circle, let's say the angle is theta here, then the point x comma y can be expressed in a way that I don't know. Actually, let's say the point coordinate is x comma y. Then actually e to the I theta equals to, right? And then actually using this Euler equation, we can easily compute the e to the I, actually, for example, like a plus b. And then because it's just a multiplying those two values, then actually we're gonna get the a plus b, and geometrically, let's say this is alpha and this is beta, and actually this is gamma, and if the gamma equals alpha plus beta, then we can get the final result just using multiplying these two values there. So this is how we can utilize the Euler equation when we compute this kind of a circular geometry stuffs. So, actually when we compute the kind of a alpha plus beta, actually we can compute this pretty easily, like this one. Correct, right? I think this is correct. Maybe? Yeah, my memory is yeah. So we can utilize the same thing for the Edward curves. So it does not have any edge case, right? So we can have only one simple rule to compute the addition of two values. If we define the addition as a addition of the angles, yeah. This is how we define the elliptic curve point addition in Edward curves. And actually, if we can also twist this a little bit to a twisted Edwards curve, like multiplying another scalar value to the term x squared. Then it will look like, before we go to that, this is how we can compute the exact the result of the point addition in Edwards curve. And if we twist this by multiplying a little bit of a scalar to the x squared term, then we're gonna have this curve, and then is slightly with a slight different term with multiplied by scalar a. And actually, this Edwards curve form can be has a birational equivalence relationship between the Montgomery form of curve.
Which type of relationship?
Birational equivalence. So we can convert this twist Edwards form of curve to these types of a where it is. These types of a Montgomery curves. Yeah. We can also convert this Montgomery form to a twisted Edwards curve form.
If we convert to like for the field and order to be the same, like when you convert to like that.
Okay, so
But what you just like one-on-one mapping or like
it's kind of mapping.
okay, so
Yeah. So it's kind of mapping. So actually, one point can be interpreted in a Montgomery form, and also one point in the Montgomery curve can be interpreted into a Edwards curve form.
So it's not the same point as the number, but like it has one-to-one on-to relation between
Yeah,
these two.
one-on-one relation with each other.
Is it one-to-one and also like one-to or just one-to-one?
It is a one-to-one relation, but actually it should use the subgroup of the Montgomery form with some cofactor. Yeah. So actually we can choose what kind of form to compute the point addition by our demands. Like sometimes actually using Montgomery form is sufficient, and sometimes using twist curve Edwards curve form is sufficient. Okay. And actually, this is the one of the most famous form that we are using. It's a Edward curve 25519. And actually, when you in your terminal, maybe recently the default algorithm to create your own public key to actually communicate to some TLS, then maybe it might use this one. And then actually we are doing the ECDH with the server. For example, you can create some public key on this curve, and then you are actually registering your public key to GitHub. Then actually you can clone your private repo in your laptop via this ECDH verification. Yeah. Okay.
So a question about the cofactor. Is it specific to a single generator? Like if I pick a different generator, that will give a different cofactor.
Different generator will give different cofactor. And actually, we have covered the Schuner signature, but actually, we can also cover the ECDSA here. understand actually how it works. It's a little bit different with the Schnorr signature, but actually doing the same thing. Yeah. We already know how the Schnorr signature works. It's a simple scalar multiplication logic.
I think it's like the first three steps are similar.
Yeah.
The fourth step is just like we are dividing it by 3.
Actually that is where the actually difference actually comes up. So you can understand that as kind of an inverse of your private, actually an inverse of the random elements. Yeah. Okay. Then now time to visit the pairing based cryptography. Okay. So let's recall about the ECDH we have covered. This is not actually a real world example, so it's not used in this way, but let's think about the case that we have Alice, Bob, and Carl, and Alice is actually has her own public key and private key, and also Bob also has his own public and private key. And they are actually communicating using ECDH there. And there is Carl, and Carl wants to check that they are communicating actually correctly. This is not a real world example. That's to say that Carl wants to check actually they are communicating correctly. Then how can Carl check they are doing correctly there? Do you think that's possible here to do that without knowing the secret key A and B? Maybe? How? Okay. Yeah. So you're yeah. Actually, we can do that. Alright. Yeah. I mean, isn't it seem difficult to do that with the knowledges that we just only covered during the morning time? We haven't covered any concept to do that.
How about signing message using the share secret key?
Signing message using the share secret key. Signing message. Actually, Alice and Bob both actually don't know about the shared secret key, small a and b.
Oh, yes.
But it's a really good point. Alice and Bob still both don't know about the small a b. They know only a and they only know b.
Yeah, not both at the same time.
Yeah. Carl also doesn't know. Nothing there.
Wait, but you said that Carl needs to know if they both get K, right?
Yeah.
So but they don't have to know both A and B to know that if they know K, right?
Actually, let's say that they have a shared secret K in A and B. Actually, this is also a both actually shared secret only for Alice and Bob.
Yeah.
And so it's not a real world example. But actually, Carl actually now checks that Carl knows K, the large K, and Carl wants to know that K is derived from
Small K, right?
A and B correctly, from which is small K is A times B, but
You can.
Go ahead.
Okay. What happens if the shared secret key gets revealed to the public?
shared secret key, this
Will it
K,
yeah.
the
will
large
it
K,
break the encryption?
yeah, it breaks the encryption. So I can see actually what you're doing.
So it should be only shared with Alice and Bob.
Right. So yeah, only Alice and Bob. Actually, this is not a real world example. Yeah. And Carl doesn't know small a, doesn't know small b, and doesn't know the small ab. Only know these 3 points.
But Carl wants to know how you get small K correctly. That's the question, right?
No. He,
Just want to know.
Carl already got a share key.
Yeah.
He wants to check if it's from big
A
A and
and
big B.
oh, big A and B.
Like it
Yeah, for example,
corresponds to
yeah.
K and things.
Yeah, he knows.
Correct.
Okay.
For example, let's say Carl is a hacker, and actually Carl exploited this shared key.
Okay.
And if Carl wants to decrypt something using this shared key, it's so expensive. So Carl needs to check these actually hacked keys correctly computed from these two public keys. This is the case.
So either he needs to get A's private key or B's private key.
Carl actually, without knowing the A's private key and B's private key, Carl only knows these three public keys.
Then there's no way.
Hmm?
Then there's no way.
Yeah, actually, for right now, we don't have that tool until now. But this is what the pairing does. Yeah, this is what the pairing does. We can check that K is exactly derived from these two values if we use pairing. Let's try to go more. So pairing is about actually doing a bilinear mapping, which means we're gonna actually map this public key to some different set with the same size. So it's a kind of a elliptic curves, but actually we're gonna define another set, which is actually exactly another group, which size equal to this number of this. The elliptical points. Then how can we say? Let's say A is mapped to, for example, let's say A star, and B is actually mapped to B star, and there exists a way to multiply both of them. And actually it will output some value, which is C star. And then if there exists some algorithm that this output is exactly same with K, then actually we can check, okay, we can map this one and we can map this to another group, and there exists some operation to multiply them, which outputs the same result to K, then actually we can check these actually K is derived from large and large B there. Let's see a more detailed example. Okay, this is the kind of a more detailed definition of the pairing. Okay. So you can check that there exists a binary mapping operation E. It outputs a element in the group target group GT if we input two different values of the group 1 and group 2. So in this case, we're gonna actually A and B are both in the group 1. Actually, there is a one-to-one corresponding. If we find another group 2 which has the same size with the group 1, then actually, okay, let's say that we have a B in group 2. Then B in group 2 can be actually expressed in form of like this. Let's say that we are just using the multiplicative form just to understand easily. But actually, it's still in the additive form. And A exists in group 1, so actually it should look like this. Then there exists a pairing function E, and the parameters we accept two parameters. One is for an element in the group 1, G g to the g sub 1 to the a, and the second parameter is g sub 2 to the b, and then it will output some value in the target group, and actually the value should return something like this.
But the G target has completely like shifted the space, right? So we are working on GT now.
To compare, when we compare it. Yeah. And then, okay, in this case, to check this key is computed correctly, send, actually this is also exists in the group 1. This is for all of these values are actually group 1 for right now, but we need to send this large K to target group.
Okay.
Yeah, and then it will be look like this. Yeah. And how to actually make this? How to send this to this target group? What about this? Like G sub 1 to the small k. We know this value, and then G sub 2 and yes. And then actually it will return something like this. Right?
I didn't get what you did after this.
Okay. So we know this one, but we would love to get this one.
Yeah.
How to compute? How to compute is that we have this pairing function, and pairing function actually have some characteristics like this.
Okay.
So if you actually receive two parameters from two different groups, then it will return an element in the target group which satisfies that G sub 1 to the A and G sub 2 to the B maps to G target to the AB. Yeah. So just simply map an element from the group 1 to target group is actually using the generator of the group 2. Yeah, because then, yeah, it makes sense, right? We can simply send these to the target group. And then what we're gonna do is that, okay, we're gonna check, this is kind of a K sent to the target group. Then we're gonna check the pairing result of these two values. Yeah.
So what is C2 there? What's C2 there?
There is C.
Is it the K?
Actually, there is another some characteristic of bilinearity that this is a pairing result, and also this is a pairing result. So we can multiply two pairing results. Then it will return a pairing result that just like the distributed load.
Okay.
Yeah.
It's like a property.
Yeah, it's a property. It's a kind of a distributed load. So if we use this property, then actually we can see that the pairing of P1 plus P2 and Q actually can be distributed into P1 Q times and P2 Q.
I'm slightly confused with the operation.
Okay.
Times.
Here,
So what is that? Yeah.
so the target group actually is not an analytical point. Target group is another group that we define. So actually, the target group had actually, this is actually this operation is defined for the target group, specifically defined for the target group. The target group is not even actually, as far as I know, actually for the curves that actually satisfy the pairing function, I don't know the target group on the elliptic curve. Yeah, as far as I know.
Can you explain one more time, like what is that operation doing?
The operation doing. So it's just a binary operation. Actually, just what we have defined when you try to define the group, just like Caesar cipher. So it's a group, target group. Target group has a binary operation like that. And if we do the binary operation in the target group with these two elements in the target group, actually it satisfies this equation.
So one is the first group and two is the second group.
Yeah. In this first group, second group, and actually this result is a target group. So we are using three different groups. So actually for one pairing function, we use just one group element from group 1, element from group 2, and its result is in the group target group GT, and GT also has its own binary operation, just like we have defined in Caesar cipher. So if we do a binary operation with these two elements in the target group, and then actually it should equal to either it's a closed. So it will return another element in the target group, which actually satisfying this condition. Yeah. So if we actually write this in a multiplicative form, it will look like this. And if we write this in a additive form, it will look like this.
So in the third line is Q target group element.
Q is a second group.
Oh,
Yeah. And this is in the target group.
yeah.
The result of the pairing function is in the target group. Yeah. So we define another group which is not an elliptic curve.
So the binary operation for the target group is neither addition or multiplication. It's like a very specific operation for.
Yeah, just like Caesar cipher we defined. It's another binary operation for only for target group.
Okay, so I'm gonna use that, the bilinearity to try to explain the car example. So what car could do is that car could take A point plus B point to get the K public point. Wait, not a plus, multiply.
No, he needs to put A point and B point into this E mapping to get the point in the T field, but then also put the K that he got in field 1 and
Group 1.
generator in group 2, and then check that the output match.
Maybe shall we try to write in the pairing form?
Yeah.
The checking Alice and Bob and Carl's case. Okay. Let's do this again. Okay, we know Carl knows Alice's public key.
Yes.
A. And then, actually, to check that, we need to send this to target group.
Okay.
We need to send this to target group. How? Is maybe actually like this.
Okay. Yes.
Okay.
Yeah.
And okay. No.
No, send me
No.
A.
I'm sorry. know A and B. Actually, we are sending this B to the group 2. Yeah.
Okay.
So B actually, let's say B star is in group 2.
Okay.
So actually, there is a one-to-one correspondence between group 1 and group 2. So I'm gonna compute its pairing result, and then it's let's say it's C, for example, and then actually C is in target group, right? A is in group 1, B star is in group 2, and then, actually CAR exploited their shared key, LRHK, and then CAR wants to send this to the target group by just doing this one. Yeah. Then it will be something kind of a K. Prime. Actually, it is in group target group, and then we are just checking this K prime and C. Yeah. And then if they actually equal to each other, then it means like K is something kind of a G to the AB, and A is G to the A, B is just kind of G to the B. Exactly same. It should be in the group 1.
So, if we get like K star or K prime or C, then how is going to be able to break the encryption?
Be able to
like decode and get the private keys.
Actually this large key itself is a shared private key.
Yeah.
Yeah. So crawl is actually just checking that the shared private key is the right one because
Oh, so it's kind of like generating the proof that it is derived from A and B.
Right. It's just getting a proof that because here kind of some assumption is that decrypting is super expensive, for example. So before you run this program, like maybe let's say you need to rent a big amount of some cloud resources, which is very expensive to run this algorithm. So you need to check before actually this is computed correctly. For example, then I found a real world example.
So,
yeah.
Is there always a target group that does that? Like, is there always an E that is there always a mapping E that can do this, or?
Always? You mean we can send any element of this group to the
Like we always construct the mapping E in this, like given
to check this.
Given to me the tape.
Yeah, we can.
Is it not only limited to pairing-friendly curves?
Only to pairing-friendly curves. Yeah.
One question I have is, so the E here, is it a pairing check between G1 and G2? Or is it just saying that E is an operation between two different groups, and then doing this operation will result in a target group here?
Yeah, it's a function that results the target group element.
Oh, got it. Thank you.
Yeah.
How do we move B to second group?
B to the second group. Actually,
yeah, do another pairing.
Is it usually that you would, instead of computing B in the first group, you would just compute A in the first group, B in the second group, and you attempt to check a third value via the target group, I would say. Is it usually like this, or do we have to move B from the first group?
they are the same group, right? Because they share the same generation to begin.
Yeah.
You are mapping it to.
Actually, if you know the secret small b, then you should be able to compute that. Yeah. In the second group too. But actually, I don't think that we can easily transform an element in group 1 to group 2.
You don't have to, right?
If we know the secret key, we don't need to. But in the case we really don't know the secret key, then actually I think actually we need to check. I think there's no algorithm to easily convert the element in group 1 to group 2. We need to know the secret value. Yeah. So because of that, in many cases, when we are using pairings, then we try to compute and share something in group 2 as kind of a shared values, shared public values. Maybe you might heard some kind of a trusted setup stuff or something. Yeah. So we share something in this via trusted setup, and we share something in some group 2 element. So we are using only those values, and we don't need to send some value to group 2 usually. So we only use a group 1 and using some given values from the group 2 and compute the pairing function and output say some target group element. Are we getting some sense of how the pairing works? Great, great. Okay. Actually, there are multiple types of pairing functions. Okay.
What was non-degenerate function? Non-degenerate.
So there's no like pairing.
So it's saying that, isn't this saying that you cannot have two elements separately that goes back to the identity, like from two groups separately going back to the identity, right? Because you can break that.
I just forgot why I just put this here. Maybe, yeah, let's revisit later. Maybe tomorrow or, yeah, if we have some ideas on that. Yeah. There. By the way, actually we have multiple types of pairing functions. And actually there are two very famous different pairing friendly curves. One is a BN curve and the other one is BLS curves. Actually, I also put some optional information here to check how the pairing really works. Yeah, but actually, I think we don't need to go deeper for all those information. Okay. Then let's just go through the applications. Where we use the pairing. Okay. So the first example is the BLS signature. Yeah, let's see. I need to revisit this again. So we have a private key, small x. Yeah, it's a scalar, and the public key, we compute the public key using the group 2. Scaling, doing the scaling multiplication using the generator of the group 2. Then it will become a public key Q. And then we're gonna sign that using our private key. To sign that, actually we're gonna actually convert some hash of the message into a form of the group element. So, for example, let's say you have some message, and then actually we can encode this message into a group element of the first group. So here, actually, small h is in group 1. This is actually you computed this from like hashing your messages, and you're making some hash of the message into a form of a elliptic curve group, elliptic curve element. Now, how we sign that? It's pretty simple. You have this one, and doing a scalar multiplication using your private key, small x. That's all. This should be your signature. Now, how to check that? Then, okay, verifier actually has your signature, and your signature is actually will look like this. And then, okay, let's try to use pairing here. You made a public key, right? You made a public key. I mean, g to the x. No, I mean h to the x. H to the x, and then we're gonna use a group 2 generator here, right? And then it should equal to group 2 generator and h. Correct? I think it's correct. Yeah. Because actually, in pairing, you can think like we can move this exponent from the first parameter to the second parameter easily.
Even if the h is not the generator, even if small h is not the generator, you can still use it, right? Because h is, oh yeah.
Yeah.
Right, because h is small t to something.
Yeah.
Right, okay, yeah.
Actually, one interesting stuff is that this should equal to this or this. Yeah. So checking these should be enough to verify the signature in using pairing. It's so simple. Isn't it? It's actually very simple.
So the
Is small x 1 to q minus 1, like the square bracket is the closed interval from the small x in a set of square bracket small q minus 1. That's 1 to small q minus 1, right? Or 0 to small q.
You mean it's including the
The
zero?
first line, yeah. Like small x.
Yeah.
It's from the interval up to small q minus 1. Like what does that square?
Yeah,
parenthesis
say
mean?
that means from 0 to
From 0, right?
q minus 1, but actually we should take 0. We should not take 0. Yeah. Just a moment. Actually, that means from 1 to q minus 1, exactly. That notation means 1 to q minus 1.
How do you determine the hash function you use? Like, because the output of the hash must be in one.
Actually, how to make, you mean how to make this message into this
How do you determine the hash function you use? Like, what kind of properties does the hash function need inside this part?
Yeah, but this one.
Yeah.
It doesn't matter here.
I think it doesn't matter that much, but actually the outputs should feed for the finite field where we are defining this PLS curve or BN curve. And because how to make this, the point is that you hash and then actually checking that, using that value as your x value, and then check actually there exists some point there. For example, if there doesn't exist a point there, then actually you need to hash that one more time until you find the point. Yep.
So we have the public key in group 2, the signing function, not the signing, sorry, the hashing function in group 1. Then the private key is where?
Private key is a scalar field. Yep. Scalar field of the group 1. And the group 2 should have the actually same size with the group 1. So the BLS curve and the BN curve actually have the same size of groups for the group 1 and group 2 in the target groups.
So the verification is checking the signature which is in group 1 against group 1, and then the result of running the function HM which is in group 1 against the public key in group 2. I don't quite get why the second check or why the second E function, it's calling on an operation on G1 to G2, but the first one is G1 to G. Is G the target group here, or?
I think G is the generator for
Generator, actually I'm sorry, this is a group 2 generator.
Ah, okay, got it.
Yeah.
Thank you.
Two is also G2.
Yeah, G2. Okay, okay.
Like I should not note here the G2, but.
So in this convention, is the second parameter always group 2?
Yep. Correct. Yeah, the first parameter is always a group 1, second parameter is always in group 2.
To make the public key to be equal to 2, you have to do the parent function, apply the parent function on x, which is the.
We can just do a scalar multiplication using the group 2 generator.
Oh, because how can we
Because you know the private key.
Ah, okay.
So you can easily create the public key in group 2. Okay, then I'm gonna give you this thing for the breakout group session too. So let's try to understand how the aggregation of a BLS signature works. It's not actually difficult because it's a pretty good example to understand the properties and characteristics of how the pairing functions. So let's try to dig into the aggregation in our breakout group session, and then we're gonna visit the KGJ polynomial scheme. Yeah, the fun part starts. The fun part starts. Okay. Let's say there is a prover P, and the prover wants to prove that. I mean, let's say I'm a prover. I want to prove that I have a polynomial here f of x, and my polynomial, the evaluation of my polynomial at value x1 is actually y1. So, for example, actually you have computed the polynomial, right? And then you evaluated that at value 9. And actually you show that you have a private key. But okay, then we're gonna show that without actually revealing what your polynomial exactly is. You want to prove that, oh, I have a secret key, without actually showing that draining by draining. You can actually prove that, oh, I have a private key. Actually, this is exactly derived from the polynomial that I computed by collecting 7 points, but actually I don't want to share what the polynomial exactly is with others. This is actually what we want to do. Okay, then actually to prove that, Wenkang is a verifier. So Wenkang actually, okay, request me to prove that. So to help me prove it, Wenkang actually picks a random number, small r, and actually gives a set of a elliptical point, which is a scalar multiplication of the powers of r there. So it will look like g and g to the r and to the r square to the r to 3 cube and to the r to the d minus 1. Actually, we should have this bracket, but yes. And then Wenkang requests me to compute. Okay, actually you have those values, so you should be able to compute this one, g to the f of r, without knowing what the random r is. Does it make sense? Just it's not about pairing. It's just about the what we have done in the electrical ECDH stuff. Because Wenkang actually share those values, but I still don't know this small r, right? But actually I know the coefficients of the polynomial. Let's say the polynomial that ZK computed from the 7 points actually looks like A0, A1x, A2 scale, A6 to the 6. And then actually ZK doesn't want to share exact value of this polynomial. But in this case, actually Wenkang actually pick some numbers, small r, and ZK doesn't know what the r is, but ZK still can compute g to the f of r by actually g to the, let's say, g to the A0, because ZK does know A0, and then multiply that with g to the A1r. Actually, ZK can compute this one because Wenkang shares g to the r, right? And then compute g to the A2 square, because also ZK can compute that because Wenkang shares g to the r square. Does it make sense? So actually ZK can compute the result of the g to the f of r without knowing what the random r is here. G to the A6, I6. Because it should equal to g to the r square, actually what Wenkang shared. And then anyway, ZK does know the coefficient.
You see, it's treating r as the x value or as the unknown, right? In this case, the variable. Yeah.
Okay. Yeah. Let's visit the case again. So ZK has his own polynomial, right? And then we're gonna test that in a random number. And then actually if ZK computes the polynomial correctly, then actually it will be on the polynomial, right? So the polynomial looks like this. Polynomial looks like this, and then we're gonna pick a random r here, and requesting to ZK that would you please give me a point, actually, which is on your polynomial? Then, what if the ZK actually cheats on us? For example, ZK is not sharing this polynomial exactly, and actually sharing another point, a random point, a random value here, for example. Then if that actually we are checking that ZK is sharing the value of the polynomial or not. This is actually what we want to do. So, okay.
So we have to figure out whether the point given by ZK is on his polynomial or not.
Yep. This is what we want to do.
But if you have a set of points that are computed by the polynomial, you can reconstruct the polynomial using the branch, can you?
You need more than
That's
one point.
true. But actually, so because of that, if you share too many information, then your polynomial will get revealed.
So you can't share.
Only a few information. Okay. And actually, yeah, this is how we make the commitment. And using this commitment, actually, we were trying to check. Actually, ZK is sharing the polynomial is on the polynomial correctly using this commitment. But ZK should be able to create this commitment, right? Without knowing the exact, the small r here is. So this is so f of r will be a kind of in the scalar field. But actually ZK doesn't know what this exact value is because ZK doesn't know small r. But still can compute g to the f of r because Wanseob already shared g to the r and g to the r square and g to the 6. And then because ZK actually knows the coefficients, then ZK can compute like, okay, I'm gonna do the scalar multiplication to the g to the r and then g to the r square and g to the r to the 6, and then we'll combine them all together like this. And actually it will return this value. Okay.
Sorry.
So does that mean in a setup ceremony, basically what we're trying to get is that setup thing, and then
Actually, we are not doing a setup. Actually, Wanseob, we are doing this in an interactive form. That Wanseob is just setting some random number r here.
Okay.
Yeah.
In a non-interactive form, the R is generated beforehand in that
It
case,
has to
right?
be discarded, right? Even on.
Yeah, actually, we're gonna handle the how to make it in a non-interactive form later.
We have to go
Yeah.
otherwise.
Yeah.
So FR is just evaluating R on that polynomial. FR is just evaluating R on that polynomial.
Evaluating the polynomial as r.
Yeah. The polynomial R.
Yeah. But actually, Wanseob doesn't want to also share the small r.
Yeah.
It's a secret value. Small r is a secret value. So instead of sharing small r, Wanseob actually sharing its kind of a public values as a form of a g to the powers of r, small r. So g to the r square, g to the r cube, and g to the r to the 6 here. So Wanseob actually share the 6 points. Yeah. Okay, then we're gonna actually prove that ZK is sharing the value correctly using y1 is a kind of secret key, which is evaluated at 9, the reconstruct polynomial. Then actually it will satisfy this condition. That's correct? So f of x minus y1 can be expressed in the form of x minus x1 times a quotient polynomial q. Because if you put x1 here, it should become 0, right? And then it means that actually we have a kind of some, we have the factor with x minus y1. This polynomial should have that factor because it's a root of this equation. x1 is a root of this equation. What makes it to 0? So it has a factor with the x minus x1, and it means that we're gonna have another quotient polynomial q of x. Okay, let's say that we have a polynomial x squared plus 4x plus 3. Then if we put minus 1 here, it becomes 0, right? So actually we can rewrite the x plus 1 times x plus 3. In this case, this is the x1 minus x1 exactly, and this is the quotient polynomial. Because if you put minus 1 here, it becomes 0. When you put x1 here, minus 1 to the x1. So we should be able to understand the relation of this factor and this quotient polynomial. Does it make sense? Why do we need quotient polynomial? Because actually we're gonna check the quotient polynomial is computed correctly at the random value small r.
Like if x1 is the root of fx minus y1, then the quotient should be a polynomial.
Then the quotient should be a polynomial.
Oh, okay.
Yeah.
Well,
Then
q of x is basically the like equation with 1 degree less.
yes, in this case,
In this case.
quotient polynomial is a polynomial a 1 degree less than the f of x here.
Okay.
So if it, in this case, in our case, the quotient polynomial should be has a degree 5.
Okay.
Okay.
5 or 6?
It should be 5 because the polynomial we reconstructed was a degree 6. And this is a degree 1.
Yeah, okay.
Okay.
Sorry, can you explain a little bit what's x1 and y1 again?
X1 here is 9 and y1 was the secret key.
Oh, yeah.
You wanted to prove x1 and y1 is not different.
Ah.
Okay. Then actually if you rewrite the f of x in this equation, then if we compute everything correctly, the left hand side and the right hand side should output the same value.
Why do we need to use pairing to compute this? Can't we just compute it with G?
Because this is about the polynomial, the equivalent relation. So for example, Zigay, would you please share me a value with your polynomial minus the value, actually the secret key, but actually you don't want to share the exact value. So you're gonna share that with me in group, for example. So you're gonna share that in group with me, and then also actually if you gave this value exactly, then actually if you compute this value, it should equal to the left hand side. So I'm letting you that, okay, would you please compute these two things separately? The first term and the second term separately. And would you please give me that in a group form?
So here, using pairings means using small g, or
Yeah.
is it another?
The reason we need to use pairing is because we want to multiply these two terms.
So who's doing step 5? The prover or the verifier?
Actually, both. Because the prover needs to give us the G to the F of R, and also prover needs to give us the G to Q of R. And then verifier will check that using G to the F of R, and Y1 is already actually revealed, G to the Y1, and using G to the R minus X1 and G to the Q of R.
So why wants to be a public?
Like there's
Y1 is already
public. That's what I'm really confused about.
X1 is secret.
X1 is secret. X1 is 9. Actually, it's not secret. It's already revealed. X1 and Y1 is
That makes sense.
Probably.
X1 and Y1 is already computing.
Can I take a step back? So
Yes.
on step 3, when the verifier requests the prover to do G to the F of R, she would know what R is. Sorry, the prover would know what R is, right?
Prover doesn't know what the R is. But prover still can compute G to the F of R because when it comes sharing those values.
But does the verifier know the polynomial?
Verifier should not be able to know the polynomial.
So if the verifier does not know the polynomial, how does, and the prover does not know R, how would the prover be
F of R by using these powers of R in the group form.
So I know G. Okay, so I would know what G of R is. How do I go from G of R to G of R?
I'm struggling to find the second group.
Actually, because you know the coefficient, prover knows the coefficient. Those coefficients. Just like ECDH, prover knows the coefficients.
In this case, so looking at number 5, right? If you're thinking about using pairing to check the equivalency of both sides, I am assuming that's what we're doing. We need to use pairing to check if they are equivalent, right? So in this case, will Y1 and X1 be in group 2, let's say, and because R, we know everything associated with R is computed on group 1, or as in FR. So one part of it, probably FR and QR will be in group 1, right? And then I guess the question is, in that equation, what part of it is in group 2 and what part of it is group 1, so that we can do this pairing comparative. Oops.
I love that.
In this case, okay. R, next one.
Yes, but they are scalar that we can put in either group, right?
Prover knows the coefficient.
Prover, only the prover knows the
Yeah, the
coefficient.
prover knows the coefficient.
So R is technically also a scalar, to be fair.
Yeah.
FR is also a scalar.
Question is I guess we have only defined one group.
Yes.
So
Yeah,
what is the
yeah.
pairing here on
So actually, it's easy to understand if the group 1 and group 2 are same. It's easy to understand because actually we actually don't need to separate group 1 and group 2, but technically we should separate them. But there's actually it doesn't matter that group 1 equals to group 2 when we think about that. So let's say that we have only group 1 group and only one target group.
Okay.
Right. Yeah. Because the property actually shows same anyway.
I guess even if you think about it in different groups, if you multiply QR into both into the brackets, right? You can technically just separate separate either things into a group in a sense, I guess.
Yeah, we need to think
so
about
it will
that.
become EFR minus Y, so EFRY1 equals to ERQRX1, right? And you can just put one of them into, in this case we can put the Y1 and X1 into or X1QR into a group 2, and then the first statement into group 1. Because it doesn't matter, I mean, you're just checking equivalency, so I guess as long as you are doing this equivalency check and putting the first thing into group 1 and the second thing into group 2, you should achieve the result you want, I guess. Assuming every step until everything you calculated it's not in a group, we can put it in a group, right? In a way, if they are not already in the group. Can I think about it like that?
Actually, I didn't get that exact your point there.
So here we are not exactly saying that what is in a group, right? So we are just trying to compare FR minus Y1 equals R minus X1 times QR. So that's the thing that we want to compare, but we are not explicitly passing in like a generator with a specific power or specific numbers of operation here, at least on number 5.
Yeah.
So based on that, what I understand is that we can selectively choose what part of that we want to compute in group 1 or what part of that we want to compute in group 2, and just thus do the equivalency check, right?
Yeah.
And then in step 2, right?
But actually, it's pretty simple that there doesn't exist group 2.
We have R.
And also, like,
You just
actually,
raise it to the power of
prover
first
cannot
order,
do
right?
step 5. Only the
And then by
verifier
step
can do
three,
step 5.
you're
And why
doing
would
the
the
same thing,
verifier
but
break
you
them
don't know what
into
R
two?
is, right?
He has all the numbers, right?
Actually, if verifier shares that, anyone should be able to do that.
But the prover
No,
knows what F
there's
of
a
R is.
small r.
Yep.
Because the F
But we,
F of
yeah,
R is
actually we haven't used pairing
so
there.
adding those terms
can do
is
it
the
in
same
a group.
as
So number 5 doesn't say it's doing
so
it
if I
in a
do
group.
G
Number 5 just
G to
tells
the
you that you are
AX
checking this
times G to
no
the
regards to any
X
group,
squared
right?
times G to the AX.
Yeah, but you should do it in a group.
Doing that is the same as G to the A plus
do it in a
AX.
group and try to complete this in a group.
Yeah.
Verify that
Because when you add those powers up, it's the
It's the
polynomial.
polynomial.
I should know this, but my brain is not working.
set to get
Is it
the
provided
values,
that
right?
Okay, let me actually
Go through again. Yeah, let's go through it.
let me go through them again.
I'm very sorry.
Let me go through them again.
Okay.
Ready? Okay.
I'm very sorry.
ZK actually has a number that 9.211 something. This is x1 and this is y1. And we would love to let before check this. Hey, ZK, would you please make some commitment for your polynomial? Okay, would you please? Yeah. Okay. Please give me an evaluation at a random number r, but I won't let you know exact random number r there. Instead of giving you a random number, I'm gonna give you the powers of the random number in the elliptic curve point form. So, okay, here's the generator, and here are 7 elliptical points, then you should be able to compute g to the f of r, because it's a g to the a0 plus a1r plus a2r squared plus a6r6, and then it's something kind of this one.
Yeah.
Right? And you can compute these just like we did in ECDH. Because if you know the coefficients, if you know this coefficient value, I already showed these values. So you should be able to compute them using just like ECDH. Okay, then ZK gave me a commitment which is a g to the f of r. Let's say this something kind of a looks like it's an elliptical point. This ZK, you gave me a commitment. Then I'm gonna test you that actually this is actually in your polynomial. And I'm gonna test that you are cheating on me or not by sharing this secret. I mean, sharing this point is on your polynomial or not. This is what I want to do. So to test that, because you have your polynomial f of x, then if we subtract your polynomial with the value you have shared with us, then actually it will return 0. Let's say this polynomial is p1 of x. We made a new polynomial, p sub 1 of x. And this polynomial will return 0 if we evaluate that at x1, which is 9. Does it make sense? Okay. So this is actually kind of a virtual polynomial in our mind. And then, you need to create p1 of x by yourself. And then actually, because it vanishes on x1, it should be able to express in a form of like this. Does it make sense? Because it should have a factor with x minus x of 1, right? And then, you should be able to compute this quotient polynomial because you know the polynomial, because you have the coefficients. Then, would you please give me the quotient polynomial evaluated at small random number r? So ZK should be able to give me a g to the q of r. You're gonna give me that. Okay, now me as a verifier, I have this one, and actually I have a this one.
You also have the R, right? You also have the R, right?
I know the R.
Yeah, you know.
Yeah, I know the R. Yeah. And then let's check that actually ZK is cheating on me or not. How to check? If this is correct, then I'm gonna create another polynomial p2 of x. P2 of x. P2 of x will look like this. This is actually me as a verifier. Actually, I create a new polynomial which looks like this, and then I can compute
Substitute that. Yeah.
this one, like r minus x1 times like this, but actually because I don't know exact value of this q of r, I only know the in the group form, so I'm gonna make this one. This is what I'm gonna do. Okay. Then yeah, this is actually what I did. And actually, if ZK didn't cheat on me, this evaluation of P sub 2 of x at R should equal to P sub 1 of x. And P sub 1 of x, actually I can also make it like, okay, G to the P sub 1 of R should be G to the F of R minus Y. Because ZK actually shared this for the commitment. And what I am doing, okay, the evaluation of P1 at random number R should equal to evaluation of polynomial P2 at random number R. If they are same, then it means that actually this exactly actually vanishes on x1 because ZK could be able to share the quotient polynomial. It means that okay, it will vanish at x1. P sub 1, this one will vanish at x1, which means that f of x1 equals y1. So we could prove that ZK is not cheating on us. So this is something kind of a, what we did here. ZK, would you please commit your polynomial? And actually, I querying that, would you please evaluate your polynomial at 9 and give me the value, evaluation value, with a proof. The proof here is a quotient polynomial, evaluation of the quotient polynomial in a group form. That's the proof. Simple. So ZK made a commitment for the polynomial that ZK has, and I am querying that evaluation at some value x1, and I got the number, and then also got the proof. And we can actually check this using pairing. The G to the P1 of R equals G to P2 of R. Actually, here, what we need to visit is the security of this assumption. Is there some potential that ZK is actually sharing some cheating value, but still actually it satisfies the pairing equation? Actually, if the size of the the size of the group is small, then actually there exists some potential. For example, let's say that we have only 3 elliptical points. Then we have actually third of a random some potential possibility that ZK actually cheating on us, but actually still satisfying this pairing condition. So this is called the soundness. The soundness is actually depends on the size of your group and 1 over the size of your group. In this case, is the actually not exactly this. It depends on the degree of the polynomial, because actually ZK sharing a polynomial, and what is the potential that the polynomial, this P1 of x vanishes to 0, because if this degree of this P sub 1 of x is 6, then we're gonna have how many roots do we have? 6 roots, right? So we can actually have some chance to randomly pick the root accidentally. Then the soundness of this protocol is something like degree. If we say the degree is D, then D over the graph. Actually, it should be a kind of Field, I mean the size of group should be the same to the size of the field, prime field of the scalar field. But let's say let's write this in this form.
So that means you should pick I mean, it's not really up for you to pick, right? Because if you're making a commitment, you need that many degrees to store that many numbers.
Store that many numbers.
Right? Like if I want to make a commitment that has I want to commit 6 numbers, then my polynomial has to be at least 5 degrees.
Actually, if you have a polynomial with a small degree, then your polynomial will get leaked pretty easily. So if you have a polynomial with kind of a very large polynomial, it's okay to share some values. So it's okay for you sharing d points, for example.
But if your polynomial is not very small degrees, you can't even do the second step, right?
Second thing?
Like having.
Oh yeah, the polynomial should be actually less than the degree of the shared powers of the random mark.
Yeah.
So
if you have that step, then if the number is a lot, then you already know that if it is a small one, you cannot specify it.
The small one cannot specify?
I mean the small degree of the polynomial you cannot specify, and then you already know it's not right to use it.
Yeah, so if the polynomial, Rank should share enough a degree of the random marks there.
So why is pairing needed on step 5?
Pairing here, step 5. Now let's see the exact pairing equation here.
Ooh.
Where is it? Just a moment, please. This one.
So D has to be big but not too big.
Oh.
Yes.
But it's cool because the prime is super huge.
The prime is huge. I think also depends on.
Actually, pairing comes here because we know actually we define 2 different polynomial piece of 2, and this is the piece of 1, and this is the piece of 2. But actually, we don't know exact piece of 2. We only know Q, what CK share, but we can compute the result of this not in the field, but in the group, target group, using pairing. Because it's kind of a multiplication of the 2 field elements, so we should be able to compute the exact same thing in target group. Okay. We have this one, and we have this one separately, and we should be able to compute the multiplication of these things in target group too. So this is why we are using pairing.
Because R minus X1 is in a different field than QR. Is that what you're saying?
No, it's something like we visited the case that Carl wants to check the shared key is exactly from Alice and Bob. So this is A, this is small a, this is small b. But actually, we know what the small a is, but actually it's okay that small, we only know the large A, and we know large B. But actually we can check that this is a large K. But actually this is small k, but we only know the large K. We know large K, large A, large B. We can do the same thing what we have done with when Carl wants to check the pairing for the explain it straight.
In this case, the y1 value is still only known by the prover, or does the prover also provide?
Y1 is a publicly
Oh, y1 is public.
X1 and Y1.
Or x1 and y1 is public.
Yeah.
Okay, got it.
And even we have R, right?
actually, even if don't know what the R is, we can actually compute that.
Yes.
Because
of the
because we know that in the group form as a large A.
I really get it.
You didn't get it? So actually, if you exponentiate this value with the group, then we're gonna have a G to the R minus x1, and we know G to the R.
Yes.
Oh, okay.
Yeah.
Because we can share that.
Yeah.
So we can still compute this in the group form. So it becomes a large A. And anyway, ZK actually share the second thing, quotient polynomial in group form.
The same thing you did there, down one.
Oh.
Yep. Yeah, that one and that. It's the same thing that
Yeah.
we can do.
It's the same thing there. So we are preparing two different polynomials and checking these two polynomials are equal by examining that at a random value R. Okay. So this is called the public coin protocol. Public coin protocol. Wenka actually pick a random. So public coin means that it's a kind of a creating a random number with a kind of a binary random stuff. So if Wenkang actually flips the coin 254 times, we can create a 254 bits of a random number. So with the public coin problem is that Wenkang actually picks a random number by flipping a coin, and then actually picks a random number R, and using that random number, we are examining that two different polynomials are exactly the same polynomial. And the potential possibility that it's accidentally same is the degree d over size of the field. And this is called the subversible lemma.
What is this one? Public crypt protocol.
Public coin protocol.
Coin. Okay.
Yes, public coin protocol. Okay. So actually, those actually the terms are something you might have heard of. So what we are doing.
Also, just on the previous slide, the reason that R is kept secret from Uber.
R
is kept secret from Uber.
Is
the value of R.
Value R is actually chosen by verifier.
Okay, but the prover must not know the actual value of R.
Yeah.
Is it what's the implication if prover knows R? Is it that they can cheat at the fourth step?
They can carefully select values to lie and make the equation
okay.
work.
But is it at the fourth step that they can cheat with this, or from the third step too?
Actually, yeah. That's a good question. Actually, I forgot the step where we can cheat when we know the random number R. But the scenario how to check that is that ZK actually sharing a commitment first. But if ZK knows what the random R is, then ZK should be able to create a fake proof with some point which is not on the polynomial. And actually, if ZK knows what R is, actually ZK should be able to do that. Yeah, actually we can, if we just say write some equations, then we may find how to do that in somewhere. So because of that, keeping R secret is pretty important.
The point is public, the polynomial is not trivial. The point is public, the polynomial is not trivial. I just want to prove that the point is
yeah. So yeah, these are something that you might heard of. The public coin protocol is that why Renkang is flipping coin and creating a random number and checking the two different polynomials at a random point is a public coin protocol. And here, the commitment what actually ZK shared with us, the G to the F of R works as a random oracle. the random oracle is here that ZK should be able to make some commitment using the random public key protocol from the public key protocol, and then it will be a reference that we can send some queries. So you can just understand Oracle is just kind of an API. So using the Oracle, we should be able to query something to that Oracle. And here, the f of r, g to the f of r works as a Oracle, as a reference. And then, when we query some data evaluation, and then ZK will share the evaluation with the proof, and the possibility, the soundness of the proof actually depends on the superphysical lemma.
The beyond is
Probability. Yeah. So superphysical lemma is what I explained here, the number of roots, and when you just pick some random number, and it can be sometimes accidentally a root that actually satisfies this equation. Yeah. So for example, P sub 1 of x will look like this. And P sub 2 of x will actually look like this. And then in x1, actually, no, it should, no. Actually, this is a case when the P1 and P2 are different. So this is kind of a fraud.
Yeah.
Right?
Yeah.
This is kind of a fraud. And actually, when you can pick a random number here, and random number here, but actually accidentally P1 and P2 are equal to each other. So that's what the superphysical lemma is. Yeah. Actually, P1 and P2 should equal, right? But this is a case, just a cheating. P1, when the case P1 and P2 are different. And when you're actually evaluating these P1 and P2 at a random number R here, and in this case, because the evaluation values are different, so we can know that, oh, this is cheating. But for these roots, there we have a 6 intersections here. Then there is a possibility that we accidentally just pick these intersections for the random number.
So the probability is missing something, right? It's the probability of this if f of x1 is not.
F of 1 actually is not exactly y1.
Right.
Yeah. Right. Yeah. I made a mistake there. So it should be kind of a, yeah.
What's the mistake? What's the mistake?
No, it's just missing one more statement of f of x1
Under the condition that
is not equal to
f of
y1.
x1 is not y1.
Yeah.
Oh, okay.
Right? Because if f of x1 is y1, then this
I-
probability is y.
Yes, yes, yes.
Yeah.
But, yep. Okay. Then I think we have covered what the pairing-based cryptography and what the polynomial commitment is here. This is the KG polynomial commitment. As we haven't covered the transit setup, but yeah, this is what the KG polynomial. And here the thing, how we make it non-interactive is that, I mean, to prove the Oracle query, actually, Wanseob needed to choose the random nonce by the public key protocol array. but actually there exists a way to create a random number in a multi-party computation setup. Because let's think about the case when we do the ECDH. Alice and Bob actually can make a shared key, but they still don't know the small AB. But they can compute the G to the AB, right?
Yeah.
This is actually how to do the multi-party computation and trusted setup. So how to do that is Wanseob actually initiated the public the trusted setup protocol. So Wanseob shared G to the G and G to the R and G to the R square. Let's say this is R1. Actually, when comes random number, and then I participate in here. And Wanseob actually doesn't share what the R1 is. And actually, I using those the first set of the generators. Actually, I'm gonna I'm gonna make this one. I can make this one because if I do this, I can just exponentiate that. I should be able to make this one. And actually, I also will not share my random R2 with anyone. And then actually, Adrian comes in, and we're gonna make this thing. Then actually, if we do not share, no one will know what the small R1, small R2, and small R3 is. So if you want to use this protocol in a safe way, just participating in it and then not sharing makes you safe. Yeah, this is a kind of a making it a real, a 100% trustless setup for you, trustless setup for you. And if you don't participate in this setup, then actually you are trusting others are not sharing. And actually, the potential that some people actually know what the R1, R2, R3 is that the multiplication potential that people are sharing their values. So if any of one is not sharing the value, then we should be safe. And if that is me, 100% safe for me. Not for you, but safe for me, at least. Because I didn't share that with people. Okay. We have covered the pairing-based cryptography and the KGG polynomial commitment scheme. And then let's have a bit of some break time to cool down our brain. And let's try to have the breakout session for this.
Sure.
Okay?
Yeah.
Right.
Oh, yeah.
We're gonna go to ECDSA and BLS signature aggregation and KGG polynomial commitment scheme.
Okay.
This is what we're gonna do.
Okay.
Okay. Let's go.
Okay.
Yeah. Maybe shall we start the breakout session from 3:30?
Yeah.
Sounds great. Yeah. Let's take some fresh air.